Okay, hello. Let's get into a paper two. We're going to go through the practice paper two together. So buckle in. I'm going to have the chapter thing set up in this video so you can scroll down to the bottom and go find the problem you are interested in seeing a solution to. Um, but yeah, I'm going to talk about some strategy, paper two strategy to start here, and how you can like use your reading time and stuff like that. And then I will go through each question pretty much in order. Which is not the way you should do the paper two, but to make navigating this somewhat easy. All right. I'll be looking at the mark scheme as we do this, so we can talk about what the mark scheme looks like. Remember, when you're looking at these, they can be a little tricky to use because the mark scheme kind of assumes you know how to solve the problem, and it's just showing you what you get the points for doing, like what parts of the process you get the points for. So this will be some more in-depth solutions than you would get on the mark scheme, and we can talk about the mark scheme in terms of what the IB is looking at. Because that's what you should be doing to practice for the paper two. So let's talk some paper two strategy. You want to do as many questions as you can. You're practicing for a big standardized test, so you should practice as many of the standardized test questions as you can practice. That's really what it is. Like, best thing you can do is just do a bunch of these, check the work against the mark scheme, see how it's going. So in terms of the paper two itself, I got the HL1 here. All of the SL questions are in here. I think there's one little thing on the SL thing that's not in here, but basically everything from SL is in here. But HL, you get 2.5 hours to do 90 marks worth of stuff. So this one is a lot. Like all of your exams, you're going to get 5 minutes of reading time at the start. So in terms of your strategy, it is unlikely that you're going to do every single thing on the paper two, and that's okay. Try to do as much of it as you can. You don't want to leave like most of it blank. But you might leave some stuff blank, and that's okay. So what you want to do is use your 5 minutes of reading time to skim each problem. You don't want to do a close reading at this point and be like getting stressed about the little details of each problem. You just want to look in general and go, oh, that's a circuits problem. Maybe I'll try that. Oh, that's a simple harmonic motion problem. I didn't study that. Oh, I won't do that one. And you want to pick the easiest problems to start with. The strategy overall is to spend the most time where you can earn the most marks. You will naturally tend to want to do the opposite. It's really easy to get stuck on a hard problem for a long time, and you can spend a long time on a hard problem and still get nothing for it. So you want to spend your time on the easiest problems because you want to get as many marks as you can get, right? You want to get as many points as you can get. So use your first 5 minutes to identify those questions that you're going to make sure you do and give yourself time to get right. And then just in terms of studying, a good way to study for this is, again, you don't need to get everything right. And you're not going to get everything right. The average score on the paper two, this is the new curriculum, so we'll see how it goes, but it seems about the same as before. And that would mean the average score is going to be somewhere in like the 30 to 40% range. So like 90 marks, the average score is going to be probably 30-ish, 30 something. Yeah, so if you're getting like 30 or more of these marks, you're doing as well as the average student. And the highest ones, like a 7 on the paper two, for whatever that's worth, is usually like high 50s or low 60s. So like 2/3, is getting you a 7. So you're not going to get them all. So again, make sure you know a couple things in detail so that you can nail them. It's way better, especially if you're just trying to just pass. If you're trying to get a super high score, you do want to be pretty well rounded and know more or less as much as you can. But if you're just trying to pass, you really just need to have a couple topics that you feel really confident about, such that you can earn like a third of these marks, which is very doable. So pick a couple things that you want to study in depth and know really well, thermal physics maybe, or simple harmonic motion, or atomic and nuclear. Whatever topics spoke to you in your IB physics journey, whatever you think you're the best at, you should study that more than the stuff you feel like you're bad at. Because again, the IB is like really good at assessing if you understand something in depth, and they're really good at assessing if you like understand the concepts. So really digging into something to make sure you really understand a handful of concepts rather than like partway understand all the concepts. The first is better. Mechanics is also a subject to definitely know in depth. Know, you know, this first page of the data booklet, you should know very, very well everything that's happening here and all the concepts behind it, because it's a very foundational. Okay, and yeah, do as many practice problems as you can. That's really what it is. You're practicing for a test. We're going to have a bunch of problems, so do as many of them as you can and get used to the IB's tricks. Do just keep in mind when you do these, your mindset should be you try to focus on understanding the concepts happening in the problems. Like doing a physics problem is not about doing math, where like just picking the right equation and plugging in numbers kind of blindly. You really, and like I said, the IB is very good at this. You really need to understand what's physically happening and how you're applying the equations to like solve what's happening. So keep that in mind. Like as you're looking at the mark scheme and stuff, try not to focus on just, oh, I did a weird math step here. Try to focus on like, why did they pick this equation? How does this equation apply to this situation? Why are they talking about this concept this way? Why are they using these specific words to answer the question? So really try to focus on that, understanding the concepts behind them, because they are never going to give you the same two problems twice. You could do every single IB exam from the past, and you'll see some familiar, similar stuff, but you won't see the same problem. Okay, all right, so that's enough about strategy. Let's try to talk about using that 5 minutes of reading time to skim each problem. So let's pretend we're going through this, and I want to just use my reading time at first. I want to just identify the stuff I want to start with. Don't get overwhelmed because there's so much on the paper 1 or the paper 2. So I turn to the first page here, and I maybe breathe a sigh of relief because I'm like, oh, a force pulling some boxes. Oh, great. Classic physics here. You can't write in the first 5 minutes. They don't let you pick up your pen or pencil, so you got to do this in your mind. But I'll cheat here and say, okay, this very first question looks like a great one to me. State the nature and direction of the force pulling this object. I'm got an idea in the back of my head, and that's just like say a thing in a direction. And determine a force. That seems pretty doable. That seems like classic physics. So there's 4 marks right away that I can at least try and feel pretty good about. Okay, number 2 then. Relativity, spacecraft, gamma, speed of light. Yeesh, relativity's hard. I might be tempted to just skip this whole problem, but I might notice the first thing is like calculate this Lorentz factor gamma thing. And I'm like, oh, well, I studied the data booklet and I know what everything in the data booklet means. And that's truly just a data booklet equation. So maybe I recognize right away, this is just like plug and chug, plug in a number and make sure you know what this equation is. All this other stuff seems like some tricky relativity stuff that maybe I won't do right away. I also have a fun, very specific little experiment that they start talking about here with a standing wave set up in a microwave and melting chocolate. Then we're going to talk about how standing wave forms and then talk about the frequency. This seems like there's a lot going on. This seems kind of tricky if I don't know standing waves really well. So if I studied standing waves a lot and I know like the definition of how a standing wave is formed, maybe I'll go for it, but maybe I didn't study waves. Maybe I don't really want to do that. Okay, then I got a satellite moving around the Earth. I'm skimming. I see there's a point for drawing an arrow. I'm definitely going to try that. That seems doable. Here's a bunch of data. Oh, that's scary fractions. I don't know if I want to try that the first time. Height above the surface. I remember those were tricky. That might be try it later. Oh, this was in Mr. Brown's video of things you absolutely definitely need to know for the IB exams for HL people is how these energies of a satellite works. And I studied them and I know them, so I'm going to do that. Okay, moving on. I see the word flux. That's scary. EM induction is maybe the hardest thing in physics, so this is generally not a thing to try on your first pass. Although I might skim these and be like, I know at least a thing to say about both of these because I kind of memorize like the thing to say when you talk about, oh, this situation and this situation. So maybe if I study that, I have something to try there, but I don't want to waste a bunch of time on EM induction because it's hard. Ooh, but here, this looks good. I know what an alpha particle is. I know how to balance a nuclear reaction. This is doable, so we'll try that. All right, maybe I'm looking at the rest of these and I'm like, ooh, black body radiation curve, surface temperature. I know that's Wien's law. Ooh, estimate the radius of the planet. I know that's like the Stefan Boltzmann law stuff. Um, you know, we did that kind of recently and maybe that rings a bell. So maybe I feel good about that one. But maybe I don't feel good about HR diagrams. All right, so you're just picking stuff that you think is easy-ish. This looks like, I skim. This looks like a ton of math. There's like a phase change and multiple phases of like heating up. That's going to be a lot. I think I know how to do, you know, heat transfer stuff, but I know enough to know that that's going to take a while. So I don't want to do that the first time through. Ooh, but this is a thing that I definitely studied, and this is a thing that I feel like I can talk about. That's a pretty common one. I'm going to come back to that. I'll try that first. I'm like, okay, draw an electric field. That is a good thing I can try on the first time. And ooh, briefly looking at that problem, that also sounds like a just plug in stuff to a data booklet equation thing. Explain why oil drop experiment. Oops, I didn't study milk and oil drop experiment. Uh-oh. All right, so maybe I won't do much with this one. Seems like they're starting to get weird talking about density ratios and buoyancies, but draw the forces acting on the oil drop. And I get to ignore one of the forces. Hooray. I can draw an FBD. I know how to do that. This seems like a whole mess. I don't know where they're going with that. But state the sign of the charge on the oil drop. I'm at least going to take a guess there because it's either positive or negative. 50-50 chance to get that 1 point, even if I don't know what's going on. This stuff is all a lot. This is like very in-depth, nitty-gritty. You really got to understand what's going on with this problem. This is not a problem to try the first time. In general, it kind of gets like that as you get towards the end too. Like some of the really weird, tricky, like very detailed stuff comes up there. It tends to. All right, so I don't know, maybe, all right, well, this is like a motion graph thing, so I feel pretty confident I can like sketch a velocity graph if I have the displacement graph. Yikes, no thank you. Yikes, no thank you. Maybe there's some, okay, thermodynamics laws, I don't know. Write a nuclear reaction, maybe I can try that. Identify, okay, fusion. I was just studying fusion. I remember this a little bit, so, and I can identify one advantage and one difficulty. I can write some stuff down at least and try it. And this one, like, maybe I would try the first time, but it looks like, to do this one, I'm gonna have to do like a lot of writing, so that might not be a first time one. That might take a while. Okay, so I used my reading time there to go through and just like mentally check off these things that I want to start with. And let's just see, I picked 2. And then I really didn't like the last part of this. 2 and then 2, so 4 marks. Just want to see how many we were able to try here. 4 marks. Got 5, 6, 7, 11, 14, 18, 20, 22, 25, right? Yep. 28, 29. I think I got like a little more than 30 already. There's 30, 34. So I just found, like, just by skimming, I see about 34 marks worth of stuff that I feel like I got a decent shot at trying and getting some stuff on. And I'm going to spend the first part of the exam like working on those questions. That's really how I would do this if I was solving this, if I was taking this exam for real. Because spend as much time as you can. If you can get most of those 30-something points, then you just pick up a couple points in all the other stuff, and you got yourself enough to pass, you know? So it's very doable. Don't let all of the everything of the paper 2 intimidate you. You really just want to come in with a game plan and like find some stuff that you can do. Study, and there will definitely be some stuff that you can do. Okay, so that's enough reading time, strategy stuff. I'm going to go through here and start doing the actual solving. All right, let's start with number 1. Be careful with this one. Take your time with the problem like this. It's mechanics, so it's doable, but the IB is always going to be very specific. It's really easy to get this one only part way right. Because I got two blocks and a force is pulling down on this bottom block, and like this block's being pulled along. So there's a lot going on, and I really want to break it down. So like, again, this is 4 marks. It's good to spend like more time than average on these 4 marks to make sure you can get them. Like really pause and think about it and draw out what's happening. Okay, so 45 kilogram block on the table. There's no friction between the block and the table. So I would maybe even sketch a little something for myself to be like, okay, that's like a frictionless surface. So I'm just trying to picture what's going on here. Then I put a 15 kilogram thing on top of the block. Force F acts on the block, so it accelerates. The thing are the same, so they don't move relative to each other. And they tell me the coefficient of static friction between the block and the object. And they're also like, this is an object and this is a block. Okay, sure. I'm going to label them maybe O and B so I can keep track of like what they're talking about. Like make sure you're paying attention to those little details, like block versus object. What things are they doing? Like take your time to get into all that stuff. Okay, so state the nature and direction of the force that accelerates the 15 kilogram object. There's 2 parts to this. I want to make sure I realize everything that's going on. State means just say the answer. No explanation, no justification, no work you need to show. And I just got to say 2 things, the nature and the direction. So nature means like, what is it? So I got to say what force is happening, and the direction is like to the left, to the right, up, down. Okay, pretty doable. Why is the 15 kilogram object being pushed or pulled? Well, picture what's going on. If you pull on this block down here, why does this come along with it? Because friction, right? There is friction between the block and the object, as they say, with the coefficient of static friction is 0.6. And so if you tug on this string down here or whatever to pull this block, this one gets pulled along because of the friction between them. And which way must that force be on the 15 kilogram object? Well, everything's moving to the right, everything's accelerating to the right. Surely the force on this object is also to the right, right? And I think that's how friction works. Yeah, it must be to the right because the 15 kilogram object is at rest, and then you pull down here and it starts moving to the right. That's the way the friction force is. You know, think about it, picture it. Okay, so it's friction. I should be specific. They said the static friction force. If I just say friction, hate to say it, the IB's not going to give it to you. So I'm cheating here to save a little time. I'm going to type and we're going to say, okay, static friction force to the right. That's it. Move on. That's my 1 point. Okay. Determine the largest magnitude of F for which the block and the object do not move relative to each other. Okay, I'm noticing right away that this is about F, which is this thing here. So I got to be careful because there's a lot of forces happening here when you got like 2 connected objects. So I need to decide how to do this. Okay, F is, there's a couple ways you could treat this. One way to treat this, and I think a good way to kind of quickly do it, is to say, let's just say whenever you got combined objects that are like moving and accelerating together, you can usually get away with this. This is really like I have a 60 kilogram object and I'm just pulling it with force F. Like F is the net force on the whole system. There's a force from B on O this way, but that means there must be a force from O on B this way. Yeah, think about that. Make sure you're okay with that. So like those 2 forces are internal to the system. So if I'm looking at one object at a time, I would account for them. But if I just like zoom out, I can be like, all right, well, end of the day, I got 60 kilograms of stuff being pulled by a net force F. Okay, so maybe that's a good way to do it. That's the net force on the system. So I could say F is the net force on everything. And I might even keep track. Which is going to equal MA. And I know the total mass is 60. 60A. Okay, so like the total force that I'm looking for, what I really need is the acceleration, right? What's the acceleration of my system? This is one way you could go about it. How could I find the acceleration? Well, what information did the problem give me? Oh, well, it gave me the coefficient of static friction between the block and the object. So maybe I can do something with this. If I want to deal with this friction, though, I now can't look at the overall picture. I need to look at one individual thing, either the object or the block. All right, so let's pick one to look at. I think the object makes sense since that's like what we were talking about here. So let's look at the forces on just the object of what's happening. And I'm pretty sure the only force happening to that object is that friction force. Yeah, that's accelerating the 15 kilogram object. This is kind of giving me a hint of what to do down here. Because like there's something accelerating the 15 kilogram object. Maybe I could use that force to find the acceleration of that 15 kilogram object. And that's the same as the acceleration of everything. And I can put that in here. So I'm picturing, and I might do this in the margins where the IB examiner won't see anything. So I don't want to put anything that's going to be scored down here. But I might just be like, okay, I got my 15 kilogram object being pulled to the right with a friction force. And okay, what's the equation for this type of friction, static friction? Well, it's not really an equation, it's an inequality. That static friction is less than or equal to the coefficient times the normal force. Well, I really want to find the maximum acceleration, so I think I want to find the maximum force, which is really all you can math out here with friction, is that the maximum force of static friction is coefficient of friction times the normal force. Oh, let me think about the normal force then happening to my 15 kilogram object. So maybe I'll actually box. Try to. And I'm pretty sure for the box, it's safe to say the normal force is equal to the weight of the box because it's sitting on top. And there's no other vertical forces. It's not true that the normal force on the 45 kilogram mass equals the weight of the 45 kilogram mass. So this guy on top of it, but for this, that's good. That's the mass of the object. Okay, so the maximum static friction force on that box would be coefficient of friction times the normal force, and I'm doing that to find A. So net force equals MA is what we're doing. Remember, with net force equals MA, it's like, it's not just force equals mass times acceleration. If you do that, you're just going to get like one force here and you might get one mark. So this means you add up all the forces on something, and that's equal to the mass of the thing times the acceleration of the thing. You gotta be really careful about what thing are you talking about. Are you talking about the whole everything thing? Or are you talking about just the 15 kilogram thing? Or are you talking about the 45 kilogram thing? You really have to break it down and be careful and take your time. So let's find, we're just trying to find the acceleration of the 15 kilogram thing here. So this is going to be like 15, you know? Okay, so this equals MA. So the coefficient of static friction is 0.6. Well, sorry, let's solve for A first. Let's solve for A. The acceleration of the object is going to be this, I'll say max, because this is like when the friction is the biggest. This times this over M object, and that's this times, oh, well, would you look at that? The normal force is the weight of the object here, so this is so fun. The acceleration is just the coefficient of friction times G. Isn't that interesting? Okay, that's the maximum acceleration because that comes from the maximum static friction force. If it accelerated any faster, this static friction would break and the box would like relatively slide backwards. So try to picture all that as you're doing this. But that's the acceleration. That's a number I can get. And then I can finally come back here and plug that in to get what I need to get. So let's do it. The acceleration then is 0.6, no units for coefficient of friction, times 9.8 meters per second squared. I'll put that over here. All right, let's see what the mark scheme is saying here for what we should be doing. Okay, exactly this. So we get 1 for just recognizing that the net force is 60 times like the acceleration we're looking for. They give us 1 if we find the static friction force. Notice they're also saying we can do it the way that we are doing it. And then when we put this all together at the end, we should be getting, 350-ish. All right, so I'm getting an acceleration of 5.88 meters per second squared. It works a little all over the place here. That's all right. All right, so the F I care about then, I'm coming back here. This is the acceleration of the object. I know from the problem that that is the same as the acceleration of the block. And so that's the acceleration of everything together. So that is the same A that goes here. The acceleration of the whole system is the same as the acceleration of the object. So I'm just going to do 60 kilograms times that acceleration, 5.88 meters per second squared. And I do believe I do indeed get 352.8. Thing. 352.8, right, which means 350. And sig figs, I think I should have 2 sig figs here. Yes, 300. Okay, lots of work really to do that problem fully. And you should take the time to do all that work because again, mechanics, like you want to study this stuff and know how to do this stuff. The big thing is they like to get you at this F equals ma. It's not just any force equals any mass times any acceleration. You really got to break it down and like what thing am I looking at whenever I do this. So take your time, be careful, make sure you can do F equals ma. That's a classic. Number 2, relativity. This is an HL question. Yeesh, okay. Spacecraft, space station, stuff is moving. These are super fun. Let's see, how do I want to start here? Okay, well, I kind of know at least the equations in the relativity section because I did the bare minimum and I studied my data booklet and I know what every single letter in this thing means. So I know I'm looking in this section of the data booklet and I know then that this is V in those equations because V is the relative speed between my reference frames. And that's always in all these problems, like how fast the spaceship is going or how fast the bus is going or whatever. Okay, the pulses are some distance apart. Spacecraft's moving, space station. All right, maybe I remember how these work, and I'm like, I usually pick a prime frame and a not prime frame, so I could say S is my, or the space station is my S frame. Spacecraft is S prime. I'll measure stuff from the spacecraft versus measure stuff from the space station and get different numbers because relativity is weird. Anyway, this first one I identified, and like if I'm really doing the paper 2, I would just do this one and then move on and come back to the rest later. But like I know that that equation is just this thing. And like V is right there. So all I'm going to do is plug this in for V to my equation for the Lorentz factor. This should be easy peasy. You know, just be careful with decimals and squares and fractions and stuff, but easy enough to go 1 over 0.8c square all of that, right? So that's like, you got to square the 0.8. So square root of 1 minus 0.64. When you square 0.8, I'm pretty sure, put in your calculator, divide by 1 or divide 1 by the whole square root stuff. Be careful. Remember, these should always be bigger than 1. You end up with a decimal less than 1. You did it upside down. It's like 1.6 repeating. Let's see. I think we should give 2 sig figs here because, yes, 2 sig figs and all this stuff. So that rounds to 1.7. And the Lorentz factor has no units. So there we go. That's it for this, Mark. It's just a data booklet equation. That's nice. Okay, again, I would like not do anything else on my first time through because relativity is hard, but let's keep going to talk about how you solve each of these. Okay, calculate for the reference frame of the spacecraft, which I remembered I'm calling S prime, the distance between the light pulses. So what's it's asking me to solve for is, oh, that's X prime. That's like, you know, what I remembered all these data booklet equations mean. That's like distance relative to somebody. Distance maybe measured by somebody on the spacecraft would be X prime. And I already know this distance, which is measured by someone on the space station, so this would be X. So I want X prime, I have X, I'm looking over here. I know I can't use these first 3 equations because that's Galilean, that's only if you're going slow. This looks great to me. Yes, okay, let's do that one. X prime equals Lorentz factor, I already found it, times X, I know it, minus V, T. Okay, I just got to plug into this now. It's 1 mark, so there must not be much else to do. The one thing I got to think about is t. T is the time measured by the person in the S frame, and somewhere up here they say that they come at the same time. They arrive at the same time according to the observers. So the time for the observer on the space station is 0. That will not be the same time. It will not be simultaneous for someone on a spacecraft. There's some nonsense about like simultaneous events. It depends on who's measuring. That's what we'll do the next one. But let's just do this. I'm going to like keep the unrounded answer is kind of the best way to do this. But you can use your rounded answer and they should give you credit either way. But I know that Lorentz factor is really like what, 5/3 or something. So I'll do it like this. Okay, x was 1200 meters minus, this is just 0 because t is 0. And so I just multiply those and I get right about 2000 meters is what I get. And then if I really want to show that I know there should be 2 sig figs, the best way to say this is this, right? But they'll take 2000 meters. That's fine. Okay, now let's find the time between the light pulses. Again, this is really just knowing what data booklet equation to use, which is this one, because I want to recognize they're asking me for t prime. That's like, again, the way they write these is sometimes weird. Like this is B, so B1 was this thing, B2 is this thing. So I want to read this as, this section is like, go back to the beginning. Oh, calculate for the reference frame of the spacecraft the time between the light pulses. I got to go back up here to remind myself for the spacecraft, so it's t prime. So I'm looking for t prime. Okay, I want to use this guy. So let's see. This one's 2 marks, so I probably have to figure maybe something else out slightly, or there's going to be a little more math at least. T minus Vx over c squared. Not much harder, I don't think, because I already know t is 0. That's still time from the person on the ship. I don't know x, and I know v. So I really know all this stuff. This one's just 2 marks because you got to do a little extra math because speed of light. Okay, so let's plug in what we know. This is 1.6 repeating. T was 0. And I'm going to subtract v was 0.8 c. Don't forget that c. It's not 0.8. It's 0.8 times the speed of light. I multiply that by 1200 meters. And I'm going to divide that by c squared. I'm going to save myself a math step here. And do that. Okay, so I got to, like, inside the fraction now, do 0.8 times 1200, and then divide that by the speed of light, which is the number in the front of my data booklet. So I'm going to finally do 1.6 repeating times 0 minus. I'm going to get a negative answer. I'll have to be careful about that and think about that. Divided by 3 times 10 to the 8. Second, that's meters. Okay. And I'm going to multiply that out and get myself an answer, which is something like negative 5.6, I think, times 10 to the minus 6 seconds. Checking over here with my mark scheme. Oh, I lied. It's 5.3. 5. Okay. Notice in the mark scheme, they're giving me credit for plugging in the values. So if you're reading these things, like the brackets mean this is sort of optional stuff. Like that's not important for the mark necessarily, but you should show your work. Okay, but like I identified like the right values to put into the equation, and then they give me a point for getting the right number. 5.3 times 10 to the minus 6 is great. If you're fancy and you know, notice 10 to the minus 6, it'd be nice to call that microseconds. Is a good one, but whatever, negative 5.6. Okay, and determine which light pulse happened first. Well, the negative is the answer here. Because remember, events that are simultaneous for somebody in one reference frame won't be simultaneous for somebody else in a reference frame moving relative to that first one. The spacecraft will not see these simultaneously. Okay, T, since we put in, see if this makes sense. Since we put in 1200 meters, T is telling me like when F happened, kind of relative to R. And it's negative. So the negative is telling me that the 1200 meter thing happened like before R, before like the 0 meter thing. And so that's what we're going to say. We're going to say F happened first. And because the answer was negative, that's all we really need here. So we're going to say because the time calculated above is negative, event F occurred first according in the yep. Okay, there we go. So a nice relativity problem for us. Let's keep going. So we can write something like the standing wave is formed when two identical microwaves pass through each other in opposite directions from either wall of the microwave, we could say. Okay, so that's how it's formed. And then I want to make sure I address the melted spots thing. There are points on the wave where there is always constructive interference. And I would like to mention, because this might give me a point, that that's the antinodes. Remember, the nodes is where like nothing happens, so that's destructive interference. So the I want to basically now just make sure I say that the chocolate gets melted at the antinode. So the most energy maybe is transferred to the chocolate at these points. So the melted spots represent the antinodes of the standing wave. Pretty good. Okay, and let's see what the important parts of that are. One is for, did I make sure that I say superposition or constructive interference? Those are the key words that they love you to talk about here. Superposition is like a good one. So I said constructive interference at least. And then energy transfer is greatest at the antinodes. There we go. Okay. All right, let's do the second part. Determine, taking the appropriate measurements from the diagram, the frequency. Okay, well, this is a hint that like, clearly I need to use the diagram and appropriate measurements from the diagram. Well, what can I measure on the diagram if I know now that these are antinodes? Okay, that tells me something. Be careful with this because the wavelength, like I'm going to get the wavelength from here. That's what it is. And to get the wavelength, it's going to be maybe double the distance you're thinking. Because you got to go like between two of them. So if it helps at all to be like, okay, if you graph something at any moment, the like standing wave looks like this. You got node, node, node. And you got antinode, antinode, like antinode. So you would have to go like two adjacent nodes or two adjacent antinodes is half of a wavelength. So you got to go like 3 nodes across or 3 antinodes across, you know, like this distance is your wavelength. That's the idea. All right, so that's your wavelength because that's like the whole cosine wave, if you want to picture it that way. So I need that whole thing. I'm going to count how many squares over it is. And it's about 12 blocks, so it's about 12 centimeters. So I'm thinking because I know the node thing and antinode thing is happening, that's about wavelength. Like I'm measuring a distance between the antinodes, so that should tell me about a wavelength something. So if I can decipher that, they're saying maybe measure the wavelength from the diagram, and then maybe I can do something there. Wavelength, frequency, that's a classic. Now I know where I'm going. Frequency wavelength is the wave equation. So I come to my topic C. I know exactly where to turn. It's the equation V equals F times wavelength. I'm like, wait, V is the only thing I don't know. Uh-oh, how fast are these waves going? Oh, well, they're microwaves. And they even tell me here, nice hint, that they're electromagnetic waves. They go at the speed of light, of course. So I just got to solve for frequency, which is just the speed of the wave divided by the wavelength, which is just the speed of light. divided by, be careful to make this meters, and I get something like 2.46 times 10 to the 9 hertz. Okay. All right, there we go. So again, they give you a range here for the wavelength. So like you can, because it's not perfect, this is actually quite generous. They let you like, your wavelength can be within 2 millimeters of that. So if you said it's 10 millimeters, I guess they'll take it. If you said 14, they'll take it. And condone power of 10 error and MP2 only. So like if you plugged in, if you didn't do the centimeters to meters thing here, they would give you the point for like doing the method correctly, but you won't get the point for the correct answer. So you got to make sure you get that power of 10 stuff right. There you go. Okay, number 4, SL number 3. We got a satellite moving around the Earth in a circular orbit. Great news. That tells me that I should be moving my mind to circular motion. Okay, and we circled this one because we said this is a good, sticks out to me on my first pass using my 5 minutes of reading time. It's a question that says draw an arrow for acceleration. I feel pretty good about that. It's circular motion. I know that acceleration in circular motion is centripetal, center seeking. Draw an arrow straight down, and I'm going to label it A, and I got myself a free point. Moving on. The following data are given. We got some mass, radius, period of satellite. Okay, both of these look like kind of a lot. This one looks like a whole lot. I gotta like do a whole derive Kepler's third law, basically. For 1 point, 1 measly point. I would not do this the first time through. I would put a star next to this and come back and maybe do it later. But let's do it. Okay, so I'm trying to get here. Remember to show that you need to, like, you can't start here, you have to end here, so you should solve and end up with this. So I need to do something. I got period squared, radius cubed, and k is like the thing. The thing I'm noticing is, I'm looking at k, and like, okay, 4 pi, big G, big M. This is circular motion. So I'm thinking around here in the data booklet, and a couple things could stick out. This is a great one, and you could do some smart stuff with this. Also, I noticed, look at this. I got 4 pi squared. I got a period squared. I bet you we could do something there. So I would start there, trying to stitch something together. And you're really just like trying to do some math, you know, trickery. So, okay, acceleration is 4 pi squared r over the period squared. Okay, all right, that's my acceleration. So I got the 4 pi squared, something happening. There's a period squared, there's an r. It's going to become an r cubed if I do this right. So I'm thinking I need a g and an m and some more r stuff. And the thing maybe that sticks out is we're talking about acceleration. There's no a in here, so I got to substitute out the acceleration somehow. And I know if we're in a circular orbit for a satellite, the acceleration is the acceleration due to gravity, because the only force providing the centripetal force there is Fg, and Fg is your centripetal force. So your centripetal acceleration is just G. So I could say this is equal to G. And I say that because I've been studying my data booklet so much that I'm having an epiphany, and I'm like, oh my gosh, little g, big M, R stuff? That sounds like this great equation that I love in the field section, G big M R squared. And if I set this equal to G big M over R squared, I think I start to see where my R cubes and such will happen. So now I've got, this stuff equals this stuff. So I guess let's solve for period squared and see if it works out. Period squared then would be, I'm going to multiply both sides by period squared. Okay, period squared is going to equal 4 pi squared r times r squared over g times m. Hey, look, we did it. We could really spell it out here just to make sure we're knowing what's going on, but that would do it for us. Gm over r cubed, so the period squared, blah, 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 r cubed. Hey, look, we just derived Kepler's third law, and we got 1 measly point for it. for figuring out all that math. Worth it? I don't know, but that's how you do it. Okay, and determine the height of the satellite above the Earth's surface. I've practiced these problems, and I know that IB likes to try to trick me with this, like above the surface, which is different than like the number in the equation, so I'm gonna have to deal with that. There's a few ways you could try to do this, but the hint is they like are having us do something in part A, and we would be smart to try to use this in part B. Like they gave me the period, and the mass of the Earth. So they gave me period, they gave me big M, and basically I'll start by finding R. So the equation we came up with seems like a great equation to use. That I could start with that equation from part A. That's usually how a lot of this stuff will go. If you're stuck, like that's a good starting point. Like did anything in the previous part? Can I build on that? Well, yes, I think we can solve for R here. And that's almost what I want for my answer, but R would be the orbital radius. So, okay, R is going to be, I'm going to do period squared times G times M over 4 pi squared. And then R is cubed, so to solve, I got to do this whole thing in cube root. So I'm going to cube root all that stuff. So I'm going to cube root, plug in, you know. Okay, 5.62 times 10 to the 3 seconds times good old big G times M is the mass of the Earth, always given if you need it. All that over 4 pi squared. I'm going to be careful in my calculator with order of operations and using the pi button and the big E button and the cube root button. Oh, so much math. If I do that correctly, I should get, what is it? Okay, I should get R equals 6.82 yada yada times 10 to the 6 meters. Okay, well, that's going to give us one of our 2 marks because that's the orbital radius, which is not exactly what they're asking us for. They're asking us for how far is it above Earth's surface. Well, remember how this works. You got to subtract the height or the radius of the Earth because I want this height, right? What I found was R, which is like a huge, huge distance way from like the center of the planet to here. Right? That's what I found. And I'm going to have to take off the radius of the Earth, right? The difference there is this height that I'm looking for. So that's what we're going to do. So let's do that. They told me the radius of the Earth, another thing that they have to tell me because it's not a data booklet. So let's just do subtract now. You'll just subtract height is going to be that one. So let's see. This is, everything's 3 sig figs. So we should, let's do it like this. 6.83 minus 6.37. They're both times 10 to the 6. So I can do this to be a little math lazy. And 6.83 minus 6.37 is 0.46. So it's like 0.46 times 10 to the 6, which is not a weird, is a weird way to say it. Let's make it 4.6 times 10 to the 5 meters, or 460,000 meters, or 460 kilometers. All are good. Okay, checking our mark scheme. We got an arrow normal towards the Earth. Remember, normal means perpendicular. We did it. Okay, this, the IB, I take some issue with here because this is a everybody problem and they're using some HL equations here. You don't have to do it this way, but this is another fun way you could do it with the orbital speed equation from the HL section of the data booklet. SL students, of course, you're not supposed to do that. It'd be ridiculous for you to do that. Ignore those parts of the data booklet, but that's a good way to do it for HL people too. Okay, we got a point for finding the actual orbital radius, and we got a point for realizing what they want, and let's go to this last part about the satellite. Okay, the satellite, we circled this one because this is on the list of things you must know because it's so weird and strange, and they like to ask you about it because it's weird and strange. How do total energy, kinetic energy, and gravitational potential energy change? Well, there's drag. The only rule that is true is that the drag force is going to take away energy, right? It's a resistive force. The force is always opposite the direction of your displacement, if you want to think of it this way. So a drag force will always do negative work, which means it'll take away energy from the satellite. The total energy definitely decreases. So I could start by saying the total energy of the satellite decreases energy as the drag force does negative work on it. Okay, and then I gotta also talk about the kinetic and gravitational potentially change during orbit around the Earth. This is the weird part. You're gonna think, oh, well, it's losing energy, so it's slowing down, right? Nope, no, it doesn't. Cause math. So study this, know this, memorize this. It's weird. Don't trust your gut for satellite questions. It's this whole thing where if you do the math, the kinetic energy graph looks like this. Then you get your potential and total energies here. And that's got to be the total, and that's got to be the potential, right? Yes, because total is that plus potential. Okay, so what's happening as you lose energy? Here's one way you could think about it. If I lose energy, like the way I would lose energy, if I start somewhere and end somewhere, I have to like go right to left here. Like this would be maybe I start here and I end here, because that's a decrease in total energy, right? From like here to here. Meaning if you lose energy, you get closer to the thing you're orbiting. And that makes sense. If you're orbiting and you lose all your energy, you will crash into the thing you're orbiting. So as you lose energy, you definitely get closer to the planet. But we know maybe from Kepler's laws and stuff that if you get closer to the planet, you go faster. And it's true. The kinetic energy increases and the potential energy decreases. It's some crazy thing that like if your kinetic energy increases by X amount, your potential energy decreases by 2X. So your total energy got smaller by X is how all the math shakes out there. Which is good to know. And I think they even want us to talk about that here in the mark scheme in a second. But let's at least say, okay, so as the satellite, maybe we can say this will cause the satellite to fall to a lower orbit. So it will speed up. Therefore, the kinetic energy of the satellite will increase. And then I want to say the potential energy of the satellite decreases as it gets closer to the planet, to the Earth. Okay, I think that's pretty good. In the mark scheme, they have some fun like little detail here about that math thing. But I want to definitely say the total energy is less. Because the orbital radius decreases, we get an increase in kinetic energy. And they're looking for this specific thing, which to me is not clear from the problem that that's like something you should say. But it is true. The decrease in potential energy is larger than the increase in kinetic energy for the total to decrease. So maybe we could add here by a greater amount than the increase, than the increase in kinetic energy. This is weird. Something like that. This would be one where like I would be surprised if many people get 3 out of 3 on this, because that last thing they're looking for is so specific. And sometimes the IB just decides they want to look for a super specific thing in the mark scheme. And that's the stupid game. That's why like you're going to get 30% on average. Yeah, I don't know. But there you go. At least know how those energies change with orbit. Number 5, we're going to do some EM induction. Don't spend a lot of time on these EM induction questions. This is one of the trickiest topics. So unless you really know what you're doing, you don't really want to spend much time here. It is easy to spend a lot of time on an EM induction problem and get none of the marks. That's just how it goes for the paper 2. So make sure you know what you're doing. But anyway, there are a couple common things in this one that are good to make sure you're generally okay with. So first, for example, outline why the magnetic flux in ring B increases. Well, I got the whole 2 rings, currents flowing through one. The other one's getting closer. Well, like they like to ask, why does flux change in this situation? Because remember, all of this Faraday magic is about flux, change in flux. And so they often like to ask, like, why is the flux changing? This comes down to the equation. I got it right here. About what flux is, BA cosine theta. There's 3 ways flux can change, is what this equation tells me. You can change B, the strength of the field. You can change A, the area of the loop, the physical area of the like ring itself. Or you could change theta, the angle between the field and the loop. Well, which one is changing in this case? It's B. The field strength is changing because B is getting closer to A, and A is the thing making the field. So let's break this down for a second and try to like look at what the heck is happening. All right, in ring A, current is flowing, as they say, clockwise, which is a weird way to say it for a drawing like this, because it kind of depends which way you're looking at this thing, but okay, fair enough, we'll call that clockwise. So that is clockwise. If I take my right hand and try to make it go clockwise, it's like, which side of this thing is the front, which side is the back? I think I see it, right? So I think it's going this way. As long as I'm consistent, I guess it's okay. The field is going to the right, let's say. Think so. I think the 3D drawing is funky here. All right, so clockwise current coming out at the top, going in at the bottom. That's what I'm seeing. So we're going to say our magnetic field is this way. That's the magnetic field created by A. Okay, and it's creating a magnetic field because current's flowing through it, and therefore magnetic field because electricity and magnetism. Ring B has nothing going on until it starts to move, but as B moves, it gets closer to A, it gets closer to this field. The field gets stronger as it gets closer to it. So that's the idea for the first one. So of the 3 things, possible answers I could have for why flux changes, in this case, it's because B changes. So the magnetic field strength through B increases through ring B increases as it gets closer to ring A. I think that's all we need to say. It gets because B increases, because the magnetic field strength increases. We could say thus the flux, how about let's say this, changes as, no, let's say thus the flux increases because that's what they're asking us. So we can spell it out and give some reasoning, and our equation here could be the reasoning, as flux is B times A times cosine theta. So I'm saying B gets bigger, therefore flux gets bigger. Sounds good. Okay, state the direction of the induced current in ring B. This is going to be the whole Lenz's law craziness. The current in ring A was clockwise. You might just take a guess here, because it's probably going to be clockwise or counterclockwise. And you might just guess counterclockwise and move on with your day, because Lenz's law opposed the change, something, something. And you would be right. You'd get a point. That's a pretty good 50-50 guess. But we can get into why. So, all right. So as B gets closer, it's the, again, Lenz's law is like the field. B is going to create its own induced current, its own induced EMF, its own little magnetic field to oppose the change that's creating it. So what's the change? Well, as B gets closer to A, it sees a magnetic field to the right that's getting stronger. How will it oppose that change? It will create its own magnetic field to the left to oppose that change, right? It's trying to fight the increasingly rightwards field lines with its own field to the left. And then if I do the right-hand rule again, now I think my current would have to come like up over the top, like so, and then down behind, and I think I would call that clockwise. No, I wouldn't. I would call that counterclockwise. Oops. Okay, I would call that counterclockwise or anti-clockwise. If you're feeling British. Okay, counterclockwise. Beautiful. Okay, 1 point, that's it, stated. Okay, now the graph shows how the magnetic flux in ring B varies with time. Discuss the variation with time and the induced current in ring B. Okay. For these two, and this one as well. There's two key things that you can always throw down if you see a random flux problem you're not sure about. This one, they're asking about, like, how does the induced current change? So I'm thinking, like, why is there an induced current? How's it going to, increase, decrease, whatever? And this one is like, why do you have to do work to make this happen? Which is a very Lenz's law-y question. That's like a common Lenz's law question. This one's about Faraday's law. This one's about Lenz's law. I could just say the key things, and the key things to say about each. Lenz's law is about the rate of change of magnetic flux. So the most important thing for me to say here, and I could truly just like write this and move on and get it probably a mark at least, is say the EMF induced in the ring is proportional to the rate of change of magnetic flux through the ring by Faraday's law. Okay, so like if you say Faraday's law says EMF is proportional to rate of change of flux, that's usually part of your argument whenever you're talking about a flux situation. And for this one, really you could say blah, 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 oppose the change. Or blah, 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 resistive force, if you remember that. Those are some key things to say. So just like even throwing something like this, don't write blah, blah, blah. Write something halfway intelligent, but, throw some stuff like this down and move on if you're not really sure, but you studied Faraday's law and stuff and memorize that at least. Okay, so let's build on this, though, to try to get all 3 marks. The rate of change of flux, the tricky thing with flux, well, one of 5 million tricky things, is that the flux increasing does not mean that there's an EMF. Remember, it's the rate of change of flux. If the flux graph looked like this, there would be a constant EMF. And so the induced current would not be increasing if it looked like this, because we're talking about the slope. So calculus fans, like EMF is, if you like, it's really the derivative, the time derivative of flux stuff. So I'm thinking about the tangent line, right? The slope of the tangent line. And so that is the EMF, like the EMF, multiplied by number of loops or whatever. But EMF is the slope of this tangent line. So be picturing the slope of the tangent line. Be thinking about the gradient when you talk about this stuff. And I know the rule for Faraday's law is that like this steepness is the EMF. So I can say the rate of change of EMF increases as the graph gets steeper. So the induced EMF increases. Faraday's law is officially about EMF, so I've now made the argument. There's probably 2 marks that because the graph gets steeper, more EMF. And I got to bring it on home with what's the difference between EMF and current? Well, EMF is like a voltage thing, and you can really treat it just as like voltage when you're doing Faraday stuff. So you can really be like EMF equals I times R, like Ohm's law basically with EMF. So I can really just say that the voltage should be proportional to the current or something. Since the EMF increases, the induced current will increase proportionally. And I'm going to say this because I know they're going to throw this in the mark scheme, and this is another one that it's maybe not obvious to say and spell out, but we can spell it out. Assuming the resistance of the ring doesn't change, which seems very fair to me. So I don't know that you need to say that, but that is a nice one to put on there. Okay, those are our 3 points. And let's go to this one now. All right, so the easiest thing to say for this when they ask you, why do you have to do work to move a thing when there's an EMF, which is a thing they'll ask you, is say, Lenz's law. So how about according to Lenz's law, there will be a resistive force that opposes the motion of a conductor when EMF is induced. Lenz's law basically says conservation of energy, yada yada, resistive force. And so let's then say, how about, since there's a resistive force, work must be done to overcome the resistive force. And move the ring at constant speed. I think something like that's pretty good. Because there's a resistive force, you got to push against it, so you got to do work. And Lenz's law says that there's like a resistive force. Okay, let's check our mark scheme and see how we're doing. Okay, magnetic field increases is good. You can also say that ring B cuts an increasing number of magnetic field lines. As it gets closer, the field lines, remember, are really denser, closer to the ring. You can picture flux as like how many field lines, how much spaghetti goes through it. Counterclockwise, we stated it. Okay, here's what they want us to say. So we have to say either the rate of change of flux increases. You can't just say flux increases. Those are totally different things. Make sure you're okay with that. So I got to say the rate of change of flux increases, or the gradient of the graph is increasing, which is saying the same thing. We mentioned Faraday's law, so therefore we got more EMF, and therefore current will increase. So here's what they say: because resistance of ring is constant. I don't know that you need to say this for this mark, although maybe they want you to. Okay, all right. And then for D, yeah, here you go. There's two things you could say. You could say there's like this opposing magnetic field that's created, or there's an opposing force, a resistive force. And so you got to do work to move against that resistive force. There we go. Okay, Faraday's law is fun. Let's keep going. We're learning how a smoke detector works, which is pretty interesting. This is really what's going on. It's a little radioactive source giving off alpha particles, and if there's smoke, it blocks some of the particle goodness happening inside, and it goes beep, beep, beep. Well, okay, there's a lot going on here. We want to read it carefully if we're going to try this one. They give me a decay constant. They tell me the size of the chamber. But there's a nuclear decay. I circled this one because we were looking at this one at the beginning and saying nuclear physics is surprisingly not so bad, right? At least this part of it is doable right in our reactions. There's a couple things you need to know, and this is another reason you would want to do this, because of course you know that an alpha particle is a 2-4 thing here, because we know an alpha particle is 2 protons, 2 neutrons. That's what these numbers always are for an alpha particle. That's going to be my first piece of solving this puzzle. I also need to know like what these numbers are. They kind of are making me do it because they say Americium 241, 241. The way we name these is the top left number. That's protons plus neutrons. And I know the thing that goes down at the bottom left is the number of protons. So I need to 241 protons and neutrons together. Take away the 146 neutrons. That's 95 protons. So the charge is 95E, so 95 goes down there. And now I can balance, now that I have the puzzle, ready to solve. So how do I make it add up to 241 on the right side? Well, this should be 237. And good old Neptunium is indeed number 93 to make it balance. Okay, so you got to know what an alpha particle is, know what the top left, bottom left numbers are. Make sure you know that stuff. The rest is a little more exciting. Outline why the radioactive source is safe for use in a house. We want to be reading what's going on. And the key thing is that it emits alpha particles. So I'm thinking about what I know about alpha particles. And the idea is alpha particles, this is kind of really where this part comes into play. They have very low penetrating power, and they don't travel like very far in the air at all before they do this like ionizing stuff and stop. So, the source of alpha particles has to be like real close to you, or, something like you breathe it in for it to really be dangerous, usually. But that doesn't mean alpha radiation is not dangerous. Alpha radiation is the most ionizing radiation. If it affects you, it's very dangerous. But the low penetrating power and all that stuff, means in situations like this, it's totally fine. So I want to say probably something about the low penetrating power. And that's because they're big, right? So I could say Alpha particles have low penetrating power due to their mass. They will not be able to, let's say, leave the chamber. That's it. Okay, deduce whether the radioactive source will need to be replaced during the life of the detector. Deduce means I gotta do something to figure out something. And I'm kind of just like also looking at the problem and being like, what else did they give me? The one thing that sticks out that they gave me is they gave me the decay constant. And I know that guy's this guy is lambda in all this stuff equations. So that's what it is. Okay, so let's see. Can that tell me something about whether it needs to be replaced? Well, yes, because the decay constant, I could figure out the half-life. The sort of implication is, okay, well, you're using a radioactive source. That radioactive source decays. And so are you eventually going to run out of this americium-241? Because after a certain time, it's going to be halfway gone. What we need to know is how long is that time? And the decay constant is what we use to figure that out. So that's going to be the first step. Let's find the half-life of this thing. Half-life is the natural log of 2 divided by the decay constant would be the move here. ln of 2 divided by the number they just gave me, which is, I got it in front of me, 5.08 times 10 to the minus 11. The percent chance of a decay every second per second. Okay, I do that math in my calculator and I get the half-life as 1.36 times 10 to the 10 seconds. That sounds like a long time. 10 to the 10, big number. I can't really wrap my head around it. We're going to make an argument here. It would probably be reasonable to think that we should do something like convert this to years. Because that seems to me like more than a year. Yeah, let's see. 60 times 365. Times 24. 60 seconds in a minute. 60 minutes in an hour. 24 hours in a day. 365. 0.25 if you're fancy. Days in a year equals something like 3153600. Seconds. That's how many seconds are in a year. So if I divide these, that's not nearly 10 to the 10. Yeah, that's 10 to the what? 6, 7? So hundreds of years. We got a half-life. If we divide them, we convert this to years, and we get that it is 432 years. So it's going to take 432 years for half of that americium to decay. Are you going to have to replace it in the lifetime of the detector? No way. That thing is going to far outlive anybody who's using it. So we could say no. And we want some reasoning, so we could say a very small fraction of the source will decay during the life of the device or something like that, life of the detector. Okay, because 432 years. Okay, and lastly, this question is crazy. I think this is a badly worded question. I don't like it at all. There's some fun stuff in here, but it's kind of kooky. Definitely, like, looking at this, you, I imagine, are not going to immediately have an idea of how to do it. This is definitely like put a star next to it, and if you're really crushing it and everything's going great and you got some time at the end, you can try some stuff here. But I'll show you what they want you to do. All right. 33% of the alpha particles that are emitted by the source enter the chamber and do this whole ion pair thing. They told us what was going on with the ion pairs in the beginning, so I should go back and read that. But it's like how it makes a current, and the current is how you know if there's smoke. All right, 33% of something, and they told me the activity. All right, here's how I want to think of it. I would do it this way. 42,000 becquerel means 42,000 decays per second. So I got 42,000 particles per second is what that first thing is telling me. And 33% of those actually enter the chamber. So it's emitting this many every second. Why don't we try taking 33% of that, right? Take a third of that. And I get 13,860 alpha particles per second making their way into the chamber. That seems like something. Because they tell me now each alpha particle has this much energy. And then they tell me how much energy it takes to form one ion pair. So I'm thinking I want to know how many ion pairs. All right, here's like, where is it? This is crazy. This is terrible test writing. This is bad. If you ask me, they should throw this question out if they put it on the test, because the alpha particles emitted by the source enter the chamber and form an ion pair. They are clearly implying here that they form one pair. Each alpha particle forms one pair, but they don't, because then down here they're implying the correct thing, which is like to form one ion pair, it takes this much energy. The alpha particle has way more, so an alpha particle is going to form many, 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 many ion pairs, and I got to figure that out. It's a bad question, but let's do it anyway. Okay, there's that many alpha particles per second. Each one has this much energy, so let's multiply those. That many alpha particles per second times 5.5 mega electron volts per particle, I think gives me, what is it? 76230 MeVs per second. Okay, that's how much energy I got going on. Now we're getting somewhere. The energy required to form one ion pair is 15 electron volts. I got 76,000 million electron volts every second. So I'm going to form a ton of ion pairs. Let's figure out how many. I think I just want to divide those, see if this makes sense to you, but I think I want to go 76,230. Now be careful, I got mega electron volts and electron volts, so I'm going to do this, because mega means times 10 to the 6. I get that many electron volts per second. I'm going to divide it, let's see if my units work here, by 15 electron volts, and that's really like per ion pair, is how I'm thinking of it. And so I'm pretty sure I'm going to get ion pairs per second here, which is 5.082-ish times 10 to the 6 ion pairs per second. Yeesh. Okay. Why am I doing that? I want to find the current, so I'm not even there yet. I want to figure out the current, and I know current is rate of flow of charge. That's the definition of current. And each time like an ion pair is produced, there's an electron that comes off, and also some kind of positive ion, they told me. And here's the other crazy thing about this question. They want just the current due to the electron. So I'm just like, I don't care about the pair thing. And the pair thing's tricky because I got a plus and a minus. So we'll think about what that even means for overall current or something. But anyway, they just say due to the electron. So I just worry about every single time this happens, you get one electron. So there would be this many also electrons per second. And now I'm really close. I need to know the charge per second. I know how many electrons are going flying through this thing every second. Well, I know the charge of an electron. It's the elementary charge. Let's multiply it to finish it off. So this many times 1.6 times 10 to the minus 19 coulombs per second is the answer, which, oops, I just had in front of me. Let's cheat. It's over here. Yes, 8.2. They write it a weird way. That should be 8.2 times 10 to the minus 10 amps. We're talking what, nano amps or something here. Little tiny, teeny tiny current. But the detector can like measure that crazy stuff. Okay, so there you go. That's the current from that. This is a ridiculous problem. I wouldn't really even try getting very far with this problem on the IB exam once I saw the craziness that was happening here. But that's how you do it. Okay, moving on. Okay, a much nicer problem. A main sequence star, a black body spectrum, some classic black body spectrum stuff. These are really good ones to know because these equations are, especially the first one is not too crazy at all. And the second one is like a pretty common combo thing that happens all the time with stars. They're almost definitely going to ask you to do stuff like this where you combine like Stefan-Boltzmann equation, an apparent brightness equation, and all that goodness. Okay, so over here we are talking about topic B. This is where all this stuff happens. These three equations are really like all of the, you know, power from radiation, power from light, energy from light stuff. And we definitely want to recognize right away if we see the black body radiation curve and they're asking me about temperature, the thing to do is to find the peak wavelength. What's the peak wavelength, right? Which is the X value where the peak happens. So it looks like 0.3-ish to me. They're going to have a range that they would certainly take here for you. I think the way I drew it on my paper, at least, yeah, I think it is. I agree here. Is like 0.31, it looks like to me. Whenever you look at a graph, make sure you're careful and look at the power of 10 stuff because that's 0.3 times 10 to the minus 6. So I'm going to say the peak wavelength that I'm reading off the graph is 0.31 times 10 to the minus 6 meters. And then I'm using this equation. And I know the regular way it happens is the temperature is this weird constant that they decide to write with units. I don't know why. Meters times Kelvin is what that means. Over this many meters, 10 to the minus 6 meters is going to give me my answer in Kelvin. So with the number I chose, you'll get a slightly different number based on whatever you read. 0.3 would be kind of lame. Try to be more specific than that. Use a ruler. Take your time. I got something like this. I'm going to not round this because it's a show that question. And a show that question means I need to show at least one more sig fig than in the value they give me. So I can't really just be like, yeah, equals 9,000. You want to show at least this is like 9350 or 9400 or something like that. All right, so always in a show that problem, ignore the sig figs. You're showing your exact answer to show that it's about 9,000. And this is about 9,000 if I round it to that, place value. Okay, next, the apparent brightness, and they give me a distance from Earth. Then they say estimate the radius of the star. They love this stuff. This is a good one to make sure you're okay with. Apparent brightness is little b. I studied my data booklet. I know that one. This is like the distance from Earth. This is going to be d in that apparent brightness equation. Then we want to find the radius of the star. Okay, well, the first thing that should definitely stick out is I have to use the equation with apparent brightness, which is b equals L luminosity over 4 pi d squared. They gave me d. They gave me b. I need to find the radius of the star, which has nothing to do with d. D is how far away the star is from us. So how could I do that? Well, the L is the thing I'm missing here. So I remember right above it, I have the good old Stefan-Boltzmann law for a perfect black body. That the luminosity of a black body radiator is the constant times A times T to the fourth. A is going to be the clue. And hey, we just found our temperature, so it seems like they're doing something here. So this is feeling good. All right, the thing you got to remember about this equation, and this thing that they don't put in the data booklet for I couldn't possibly tell you why, is that A means surface area. They don't give you the equation for the surface area of a sphere. So you need to know that it's 4 pi r squared for the surface area of a sphere, which is what a star is. Okay, that's how I'm going to get my thing I'm solving for in here. I'm solving for this radius of the star. This all goes in for A. This all goes in for L. Let's do lots of math. All right, B equals the luminosity, this, over 4 pi d squared. Okay, A itself, I'm going to cheat because I don't have a lot of room. A itself is, let me just do this all at once, 4 pi big R squared times, okay, what did I lose? T to the fourth over all the other junk. The 4 pi's go away in this, which is a fun little thing. And like I just solved for R, you know, do some algebra, square root. This is like a good time maybe to be like, I'm going to come back to this because now I got to do a bunch of math and plug a bunch of stuff in my calculator. And maybe I don't feel like I have time right now. Maybe I'll get most of the marks if I just showed this work. So let's just solve for r, which I'm pretty sure will get us 2 of the 3 marks. I just do some algebra here. If I can do algebra correctly, maybe. Square root. Yes. Okay. All right, and then let's plug in the numbers, you know, but that's just going to be our last one measly mark. So we know B, it's this number. Oh, sorry. Backwards, B is this number, 2.2 times 10 to the minus 9 watts per square meter. Okay, watch out for kilometers because constants usually have like the meters thing baked in, so we wouldn't try to always work in meters. So 10 to the 14 kilometers would be 10 to the 17 meters. Yes. So let's just do that so we don't mess stuff up. Okay, 6.2 times 10 to the 17 meters, and I want to square all that. This is why this is like a maybe do the algebra and then save the math for later, because if I make a mistake in any of those little things, if I don't get kilometers to meters, if I forget to square all this, if I type it in my calculator wrong and don't square it right, you don't get this mark for doing all this math and all this calculator stuff. It's worth doing at the end because you'll probably have time at the end where you're like, oh my gosh, I got nothing left that I can possibly do. I don't know anything. I'm going to fail. And you're, you know, spinning out. That's when you come back to a question like this and you're like, oh yeah, I know how to do math in a calculator. I can do that. And then you'll get it right and you'll feel confident and you go find more questions and you're like, oh wait, I actually do know some physics. And then you'll pass the exams and you go move on with your life and things will be good. Okay, this all turns into, if you do it in a calculator, right, 1.5 times 10 to the 9 meters. I think if you use the unrounded, like 9,300, whatever, you get 1.4. They should take it either way, especially because, like, they gave you this, so you can use this in part B, even if you can't solve part A. So anyway, there you go. That's what you get for this guy. And lastly, the radius of the sun is this much. Sketch on the HR diagram the position of this star. This is like a thing that they are, I think, adding this year is these, so it's almost definitely going to come up. An HR diagram has been there, but the whole like lines of constant radius they're stressing this year. So remember how these work. If you have your weird HR diagram, remember temperature goes backwards and we got luminosity on Y. Like stars on these diagonals would all have the same size. So, and be careful reading this because like, okay, that's 1,000, that's 100, and then like that's 10. It's like over the line, then underline. So that's, this line is where a star along this line would have a radius of 1 times the radius of the Earth. A star along this line would have a radius of 10 times the radius of the Earth. Well, I need to figure out probably how big our star is then. They told us the radius of the sun. And in the previous question, I just figured out the radius of the star. Well, let's just divide him. Again, be careful with the kilometers thing. So the radius over, let me do it down here. The radius over the radius of the sun is the number I just got, 1.5 times 10 to the 9 meters divided by the sun is 7.0 times 10 to the 8 meters, right? 10 to the 5 kilometers is 10 to the 8 meters. And that is like 2, give or take, 2 and change, right? It's like close to 14 over 7, so it's about 2. So the radius is about 2 times the radius of the sun. That is plenty detailed enough for us to try to plop something on this sketch. So it's going to be just above this line is what I want to go for. And I want to plot a point, like where the position of the star is, because the position of a star is just a point based on its luminosity and temperature. I don't know the luminosity, but I don't need to because I know the radius now, and I know the temperature is like 9,000-ish. Temperature is under 10,000. Be careful. Under 10,000 is to the right of 10,000 because there's 5,000. You know, so watch out for that. That's annoying, but that's what it is. So we're going to go here-ish, in an ideal where you actually like use your ruler and measure and like get a good sense of where 9,000 is. And then we're going to come a little bit above the 1 radius line. And I'm trying to, more or less show this. And it would be very smart to label this. That is about 2 times the radius of the sun to show like I know where I'm plotting it. But that looks pretty good to me. Okay, let's do the mark scheme thing just to check what they are looking for specifically. So correct substitution into this equation, or 9350 Kelvin. So they are pretty stingy with what they're looking for there. Again, you got to read that peak really carefully. You should be getting a number here that gives you, would round to like 9350. Okay, if you're off of that, they are unlikely to give you the mark. So really be careful reading your radius. This one, though, they take a range because of that temperature thing. Okay, but so this is nice. If you attempted to use this equation, they give you a mark. They don't always do that, but they were feeling nice here, so that's good. Then if we use this equation, we combined it with the luminosity radius Stefan-Boltzmann equation. That's 2 points right there. So we did really earn 2 of our 3 points just by doing this stuff before we did all that math. But all that math tells us 1.4 gigameters if you want, because that's a giga. Okay. All right, and for the last one here, you do have to show somewhere in your work the radius you calculated. If you just plot it on the graph, they're gonna just give you 1 point, it looks like. Or I think if you plot it in this zone, you are showing, maybe, I don't know. This is questionable. This is a little also sketchy to me, haha, that the command term is sketched, but they also want to see this. So just to be safe, it's good to include, but we just want to plot in this region and we're good. Here we are with number 8, SL number 6. This first part is another deceptively tricky problem that like would take a long time. Part A of this is a bit of a trap, I would say, on your first time through, because there's so much happening. If I start picturing what's going on with like temperature changes, phase changes, temperature changes again, it's like a mess. It's going to be so much math to do here. There's a ton of work that goes into getting these 3 marks. You can get some partial marks without too much difficulty. So, we'll go through it in a second. But that is also, I would not do it the first time through. I would jump down here and be like, oh, I know I'm going to talk about heat loss to the surroundings and stuff. And like these 3 marks are way easier and quicker to earn than these 3, I would say. Okay, so anyway, though, we're doing a little calorimetry heat transfer thing here. These are tricky because you have to really think about what's going on and apply it. This is not a cookie cutter, there's an equation for this kind of thing, really. The equation for this really is Q lost equals Q gained with a negative sign on whatever side you feel like. Because it's really just, there's no change in energy. All the energy stays in the system. So like anything gaining energy, anything losing energy, one is giving energy to the other. But there's so many different situations that happen here. This is not just MCAT equals MCAT. There's way more going on. We got to think about what's going on. Okay, so what's losing energy versus what's gaining energy? Well, the losing energy is maybe a little easier. So I'm trying to picture what happens. I have like wax, like cool wax mixed with hot wax, and you stir it until equilibrium's reached. So the hot stuff is going to cool down, right, to like melt the solid stuff. And then it's all going to equalize. So in terms of lost, Q lost is just going to be like the energy lost by the hot liquid. But the stuff being gained, like let's think about the total amount of energy gained by this 30 grams of paraffin. There's a couple things that happen. It starts at 42 Celsius. The melting point is 47 Celsius. Okay, so first, I need to remember how this works. Like you increase temperature, then you change phase, then you increase temperature, then you change phase. And we got to do 3 of these things just for gained, because it's going to heat up to 47 degrees Celsius. Then it's going to change its phase. Then it's going to heat up to whatever my final equilibrium temperature is, and I'm going to have to figure that out, and it's like a ton of math to do that algebra. But let's like try to account for what's going on. So I would try to kind of keep track and be like, okay, I'd be like, how much energy, Q, heat energy, to turn the solid thing, to heat it up to the melting point. So to go from 42 Celsius to 47 Celsius. Well, that amount of energy, MC delta T, tells me how much energy it takes to change the temperature of a something. So that much energy would be 0.03 kilograms. I'm being careful to like do everything in kilograms because kilograms. Times 700 joules per kilogram is how I kind of think of this because it's kilojoules. Times 5 Kelvin. Going from 42 Celsius to 47 Celsius is a change of 5 Celsius, which is also a change of 5 Kelvin, right? So either way, that's good. That's how much energy it would take first just to heat the thing up to the melting point. Then I got to melt it. So how much energy does it take to melt it? Well, that's Q equals ml. That's equation just tells me how much energy it takes to melt or change the phase of a certain amount of stuff. All right, so these equations all vary, like you got to apply them. They just tell you how much energy different things cost. And you got to think about what's happening to add up all the costs. Okay, I still got this many kilograms, and I just multiplied by L, 220 kilojoules per kilogram. So I will do it like this. You could do everything in kilojoules if you like, just be consistent. You'll get the same thing. That's 6,600 joules. Oh, I should have put this here. This is 105 joules. This is one where I'm going to do like the math as I go because it makes more sense to me to keep track of like the amounts of energy to picture what's happening. Okay, and then let's see. The paraffin at 47 Celsius heats as well, heats to like whatever the final temperature of the mixture is. And that's going to cost me MC delta T worth of energy. And this I don't know yet. All right, those three things all have to happen to the solid paraffin, though. And where does all of this energy come from? It needs 105 joules to first heat up to the melting point. It needs another 6,600 joules to melt. And then whatever extra energy it gets is going to heat it up to some middle-ish temperature. And where is it coming from? It's coming from the hot paraffin, the liquid paraffin that's donating all this energy to the solid stuff to heat it up, melt it, and then heat it up more. As that happens, this is getting cooler because it's giving off its energy. So the Q lost is the energy lost by the 150 grams liquid paraffin going from 240 Celsius to whatever final temperature. Okay, that's me trying to picture everything happening and tally up all the energy. So I'm going to do negative Q lost equals Q gained then is how I like to do these. And the negative like makes it so that the change in temperature things work out when you do final minus initial, or else it gets weird. All right, so Q lost is negative MC delta T. In this case, the mass I'm using is the mass that's giving off the energy, which is the 150 grams, aka that many kilograms. And I would multiply that by C. And I got to be careful. I got two specific heat capacities, one for solid, one for liquid. Oh boy. Well, this one is liquid and it's cooling down in the liquid state and it's going to stay that way. I'm doing joules, so let's be careful that this would be 2130 joules per kilogram Kelvin times the delta T. And here's the trick. Delta T is final minus initial. The final, I don't know. I'm just going to call it, let's call it T final. Minus the initial. I'm going to keep it in Celsius because it's all delta T stuff, so that's fine. You can do that. And that was 240. Remember, delta T's, Celsius is fine. Just T, you got to use Kelvin. Okay, and that equals now. Okay, so that like lost this much energy. That's how much energy did all of this stuff. So that should equal, I already did these, so I can just add them up. That should equal 105 joules to heat up the thing, the melting point, plus 6,600 joules to melt the stuff, and then however much more energy until they hit the same temperature. Let me put in some numbers here. So the mass here that I want is the first mass, which was 0.03 kilograms, times, now I got to be careful. Think about what's happening. Okay, this is a liquid now, right? This is the energy to heat the liquid paraffin that just melted from the 47-degree point that it melts at all the way up to whatever final temperature. So I'm going to still use this liquid specific heat capacity. Running out of room. Times the final temperature minus the initial temperature of this was 47 Celsius at that stage. Yikes. Okay, there's a whole lot going on here. It's very easy to lose track of something along the way. It's kind of a miracle if you can do this without making a math mistake somewhere. And this is a crazy amount of work for that last point here, because they're going to give us a mark just like if we did two things right in our setup in like these two stages. So again, this is like, don't spend your time doing all this math if there's stuff you haven't gotten to yet. But a star next to it, come back and do the math later. It's not, I don't know if it's worth it to get a point for all this. Screw any piece up, you don't get the point. Yeesh. Anyway, you gotta like distribute a bunch of stuff. It's a mess because the trick is, right, you get a number here, you gotta distribute it in. And then you get two different terms with t. So if I do that, I end up with, okay, so I guess this number is 319.5 times the final t plus, because minus times minus 76,680 equals, let's see, I got 67.05 here plus 63.9 is what I get when I multiply this. I also distribute that to the t, and I then take away, because I'm subtracting 47, so this times negative 47 is this. We're not even done yet. We got the TF here. The TF here, I got to combine like terms. And then, I think I get this equals negative 7, dude. This is just crazy. This is too much work for one point. I wouldn't do it. I would have bailed long ago. But you get something like 190 when we round it. So 190 degrees Celsius, because I've been working in Celsius. Yeesh, okay. It took us that long to get 3 points. Let's get 3 more points. When the experiment was carried out, the equilibrium temperature is different, suggests the reason. Whenever they say this, don't even think about it. Heat lost to the surroundings. That's the reason everything in calorimetry happens. There was, let's say, some heat. How about this? Some heat was lost to the surroundings during the experiment. It's 2 marks, so I must have to say something else. I could maybe explain a little bit how, but it's pretty clear. They do say the equilibrium temperature of the mixture was found to be different, which is kind of a clue that I think they are hinting that they want us to explain, like, which way. The final temperature of the mixture would therefore be lower than the calculated value, since heat energy left the system. That should do it. Okay, the mixture was held in a large metal container. Metal, I'm thinking metal, to do a heat lab. That's silly. It's very conductive. Explain one change that could happen. Insulate the container. That ought to do it, right? Use an insulated container. Use something with a lower specific heat capacity. Cover it with a lid. Say something like that. Hey, look, we just got 3 points. Those 3 points are worth just as much as these 3 points. Make sure you get those points. Okay. What are they looking for in the mark scheme? Let's mark scheme this to see, like, decode what the IB is trying to do. Okay, here they have the whole set of like all the different terms you have to add up and account for. The way they mark this is pretty nice. If you have one heat capacity term correctly substituted, you get a point. So if you did any one of these things, if you realize you needed to like, you know, um, like do this part, if you multiplied those three numbers together, you get a point. Or if you realize you needed to do like this, you get a point if you have those things multiplied together. Or if you multiplied that stuff together, you get a point. So if you did any of that heat stuff, you're good. And then the other point is if you did the latent heat thing correctly, like you realized that there was melting happening, you need to account for that. So if you're multiplying those two numbers together somewhere, you get a point. And then you get the last point for all of the math and getting to that answer at the end. Okay. Okay, and indeed, our 2 points here are the experimental temperature would be lower. So I want to explain the difference and say why. Because of heat loss to the environment. That's it. Heat loss to the surroundings. If they talk about heat stuff, say that. Okay, these are 3 different things you could say. Insulate the container. You could do it quicker, so less heat is lost, I guess, during the time, or use larger volumes of substances. So proportionally, like, I guess your heat loss doesn't matter so much. Okay, cool. There you go. That's number 8. Let's keep going. And let's do number 9, SL number 7. These last couple problems are a doozy. They like to sometimes throw some of these super long multi-part problems at you. So you can definitely jump around. Like a lot of times you can do later parts without doing the first parts. So as usual, you don't need to work in order. These do build on each other a lot, so kind of do your best to at least keep track of what's going on. But these first 2 parts should be pretty straightforward. First, they want me to draw the electric field line between 2 charged parallel plates. I'm so happy I studied this. I memorized my field line patterns. So we're gonna go. Let's go medium. Okay, you want to remember for charged parallel plates, there's a uniform electric field in between the plates, which means you need evenly spaced, perfectly straight lines up and down. And we do also want to show the edge effects, they call them. Doing my best with my little tablet here. You will, of course, use a ruler to draw these as accurately as possible. Don't lose a point because you don't want to draw a straight line. Okay, and then you do want to show like the kind of fringing around the edges. This is kind of sloppy, but something like this. And then we're going to show that the field lines point from positive to negative. That's the field line pattern for charged parallel plates. You got to know it. Know all your field line patterns. Field lines point from plus to minus, from high to low potential. Throw an E on there just for fun because that's an electric field. Okay, then they give me the potential difference between the plates and the distance between the plates, and they say calculate the electric field strength. They've been beating me up with some of this paper 2 stuff, but this one is a gift because I studied my data booklet, and that's literally just a data booklet equation. The electric field strength between 2 parallel plates is the voltage divided by the distance between the plates. All I got to do is 960 volts divided by 8 millimeters. Let's turn that into meters. Millimeans times 10 to the minus 3. I divide, I get 120,000 volts per meter, aka newtons per coulomb. That's it. That's 2 points right there. Think of all the hard 2 points you earned. Make sure you get those 2 points. Okay, moving on. Now things start to get a little weirder. We're going to tell you that oil drop experiment, Millikan's oil drop, is an experiment they want you to know about. It's a good one to study. It's how we learn some stuff about charge. So first, the oil drop enters this region between the plates. The plates don't matter yet. The plus minus doesn't matter yet. It moves between air in a tube before it falls between the plates. As it falls through the tube, before it gets into the whole place where the electric field is really happening, how does it become charged? Well, really, it's just friction. How does anything become charged? It becomes charged by friction. You rub your socks on the carpet, that is going to charge it up because you're just moving electrons. Remember, everything is covered in electrons. Friction. Everything's covered in electrons, and like with some rubbing, with some friction, you can pull a few electrons off or add a few extra electrons. And just that little tiny imbalance gives you a net charge. You know, this oil drop might have a jillion electrons, and it's got a jillion little positive charges in the nucleus of its atoms too, so it's got no net charge. Well, if there's some friction and it picks up a couple extra electrons, it might have a jillion and 2 electrons and just a jillion protons in the nucleuses, and then you end up with a net charge. That's how it works. So it's just friction, perhaps between the drop and the tube, and or air will transfer, maybe can transfer charge to or from the oil drop. Friction, I'm thinking, is probably going to be the key word there. Okay. The oil drop is observed to be stationary in the space between the plates. Buoyancy is one of the forces acting on the drop. The density of oil compared to density of air is given to us. Show that the buoyancy force is much smaller than the weight. They're going to try to convince us that we don't need to worry about buoyancy force. Okay, the whole buoyancy thing here is really like complex, surprisingly complex, what they're going to get into with this problem. It's pretty nutty, but so here's what they want us to do. They want us to first know, the first thing you want to know is what's the equation for buoyancy. Buoyancy is the equation, density, volume, acceleration due to gravity. But like all equations, you got to think specifically about what all those letters mean. Density, yes, but what density? Volume, yes, but what volume? Well, for the buoyancy force, it's like the usual case is you have like, you know, a rubber ducky or something. You got something like in a fluid, and there's a force like a floaty force. Buoyancy is like a floaty force, right? Up. In this one, it's like the variables are really about the fluid. So density is the density of the fluid that you're submerged in, right? If you're submerged in water, that's different than if you're submerged in any other given liquid. And V is the volume of the fluid that you displace. So in this one, this is the density of the thing you're submerged in. What is the oil submerged in? Well, it's submerged in air. Yeah, the oil is like kind of floating in the air, and it's so small that buoyancy force from the air we might care about talking about at least. We're going to see here it's really small. I'm going to put a little A here to remind myself that that's the density of the air. And that's how I'm going to work in something like this. The density of the oil is 730 times the density of the air. Okay. Well, that's the buoyancy force. What about the weight? What does weight mean? Weight means force due to gravity, and I know how to find force due to gravity. It's, of course, in my data booklet. It's just m times g. Now, I need to show that m times g is way bigger than this. I gotta kind of think a little outside the box here and do a little trickery. I know I need to get like density of oil in here somehow because they're giving me this. So mass, density, there's something there. Density is mass over volume. So one fun way you can do mass, and this is really where the buoyancy equation comes from. You want to look back at how we derived that. But anyway, one fun thing you could do is like density times volume for mass. So the mass of the oil drop is also a density times volume thing. But again, think about these letters. What do they mean? This would be the density of the oil. Right? The density of the oil is the mass of the oil divided by the volume of the oil. So now I got my density of oil. This is mass. And so the weight is equal to density of the oil times the volume, because that is the mass, right? Times G. This is not a buoyancy force. This is the weight of the oil droplet. And this is the buoyancy force because that's the weight of the water, or sorry, the weight of the air you're displacing. So if it helps to remember the whole Archimedes principle of what the buoyancy equation really is, The buoyancy force is equal to the weight of the fluid you displace. So we're doing weight with density and volume 2 times with different things. Weight of the fluid, weight of the drop. Okay, now I want to show that one is much bigger than the other. Oh boy. Let's do a ratio. I like a ratio. What if I did FB over the weight? What's this ratio equal to? I bet you really, really small. The buoyancy we said is the density of the air times volume over G. Down here we got density of the oil times volume over G. That distinction is really important, right? These aren't just letters. This isn't just math. Yeah, know what all this stuff means. Easier said than done, I know. Okay, the volume is the same because it's the volume of the fluid you displace. And then here's the volume of the oil drop. Well, that's the same amount of space. G is G, those go away. So this ratio is equal to the ratio of the densities, which is what they told me, is 1 over 170. No, 730. So in other words, this equals 1 over 730. So if I really want to spell it out, I could say, so the buoyancy force is like 700 times less than the weight, which is why we can ignore it. Okay, so there you go. Lots of fun going on there. That's super complicated. That is maybe hard to kind of figure out on a paper 2 on the fly, but that's the idea there. Okay, now we want to draw the forces acting on the oil drop, ignoring the buoyancy force. I got to remind myself what's going on here. The oil drop is stationary in the space between the plates. So I want to come back up to my first picture and be like, what's even happening here? Oh yeah, there's an oil drop. And some oil drop, this is how that experiment worked. The oil drops will all get different amounts of charge. And for some of them, the charge will be just right that they can hover. If there's an oil drop hovering here, how does that work? What forces are happening? Well, definitely don't forget about the weights. The actual weight of the oil drop is this way. What's the force holding it upwards? It's going to be the electric force. Yeah. There is, so what they're getting at is there is, even if it's not moving, buoyancy, a little tiny bit of buoyancy force from the air, because the oil drop is kind of floating a little bit in the air. But what we're saying is this is so much smaller than the weight, I can really ignore it. So we're going to ignore that, and we're just going to draw those two forces. So I need to draw that I know that there's definitely weight. There's a force due to gravity pulling down on the droplet here. And I'm going to draw that as a vector straight down. And I'm going to label it with like a W or an FG. And there's also an upward force, which is an electric force. And I want to show that that's upwards. And I also want to show that since this thing is just floating in midair, that these two forces are the same size. All right, draw them nice and straight up and down, but that's as good as I'm getting with my little tablet here. So I got the electric force, Fe, this way, and gravity this way. Okay. Continuing on. Show that the electric charge on the oil drop is given by yada, yada, yada. Where this is the density of oil, V is the volume of the oil drop. Okay, this one's pretty hard to do if you didn't do this part and figure out the whole, density of oil times V times G is not buoyancy force. This is not the buoyancy force, because that's not weight of the air being displaced. That's the weight of the oil drop itself. Because density times volume is mass. And what are they getting at here? Well, I noticed the E and the Q, and I'm thinking about my data booklet, and that brings an equation to mind right away. That's kind of the definition of E, electric field strength. It's force per unit charge. That electric force I just drew, the up force, I got a force this way, the electric force. And that's Q times E big. I got another force this way. Fg is M times G big. Those two are going to be the same. I think that's what they're doing here. So I could start by saying something like the electric force is equal in magnitude to the force due to gravity. So Q times E equals M times G. Mass of the oil drop, I see what they're doing here now, is the density of the oil times the volume. And I'm going to have to put that in here. And then solve for Q. So this would be enough to now just show the answer. It's just like algebra steps. So Q is rho of oil times G times V over E. I showed it. And state the sign of the charge on the oil drop. Well, let's picture again what's happening. There's an electric force upwards. I want to go back to my first thing of the plates. What kind of charge would be pulled upwards by a positive and pushed away by a negative? That sounds like a negative charge to me. So we're going to say negative. This is a great question where if you were looking at this whole thing and you're like, oh boy, the oil drop experiment, I didn't study it. I forget how buoyancy works. This is scary. You see this one and you can at least flip a coin because you know it's going to be either negative or positive. So we'll say negative. That's all I got to say. State it. Okay, we just keep on going. The electric field is now turned off. So I'm reading that. I'm like, okay, I'm thinking about what that means, about what's going on in the situation. Now there's no more electric force. No more Fe. So now the drop is just feeling the force due to gravity. And like the moment that I turn it off, the drop falls vertically, reaching a constant speed V. And I'm like, oh, terminal speed, terminal velocity. That's what that means. It falls, and as it falls, it accelerates, but it accelerates like slower and slower and slower because there's going to be a drag force that gets bigger and bigger. Just a little bit at the beginning, and then more, the faster it goes until we have another situation where the drag force will equal Fg. You want to know this is how terminal speed works? Outline why for this drop, this equals this, where this is the viscosity of air. Constant speed, talk about force stuff. A great thing to say here would be, I know that constant speed means zero acceleration. This is one where I think you could probably do it with a combination of like writing and or equations. I think we want to say, since the oil drop is falling at a constant speed, the vertical forces acting on the oil drop must be balanced. Therefore, the weight of the drop is equal to the drag force opposing its motion. And I could even maybe, if I want to really spell it out and make sure, I could say, so the drag force is equal to gravity. Drag is, that's just the equation for drag, right? Viscous drag, RV, and Fg is mg, which we already showed is like this whole density volume thing, right? So they are equal. Okay, another like kind of complicated one where if you talk about buoyancy at all, they're not going to give you anything because this is not buoyancy. That's the weight of the oil drop. Weird. Okay, more. Show that the charge on the oil drop is about this much. They give me some data like these. This is where you want to recognize a lot of times they're building on previous stuff. They just gave me this equation. They're giving me R and A to the viscosity and V. And I had this equation and they're asking me for Q. This has a Q in it. I bet you I can just take this and plug into it. That's what they're hoping I do. Be careful with, I got a big V, which is the volume of the oil droplet. And then I have a little v over here, which is the velocity that it falls at, the speed. So 6 pi. Okay, and you know what? The trick here, actually, looking at it, we're kind of stuck because we don't have a Q. And I'm trying to find the charge on the oil drop. So I want to even go back a little bit because we have three different things that are kind of equal that we've set up. So these were equal when it was falling. When it wasn't falling, these were equal. So there's my Q. Q times E equals the weight of the oil drop, which also equals the drag force on the oil drop as it's falling. So all of those things are equal. That's like what all the work we've done throughout the whole problem put together. So I want to find Q, and now I know this stuff. So that's going to be the move, is that Q, the charge of the oil drop, is yada, 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 divided by E. We just plug in these numbers now. So let's do it. So 6 pi times this guy times R is this. Micrometers, don't miss that, 10 to the minus 6 times V. Do make sure you stay inside the boxes when you do this best you can. 140, also millimeters, 10 to the minus 3 meters per second. Okay, and then I divide all of that by E, which we found like a long time ago, right? We found a long time ago it was 120,000 volts per meter. This is the big conclusion to all of the work we've been doing, our equations, our electric field strength. Yeesh, okay, you plug it all in and you should get Q equals, and it should work out to about this. Do remember with the show that problem, when they give you the answer, you have to show it to more sig figs than they give you. This is the one time where you don't follow sig fig rules. So you need to show at least 3 significant figures to show that you actually got an answer that rounds to this, not that you just like didn't get the right answer and you're just, hoping to throw a Hail Mary and just write 4.8 and hope nobody notices. You got to show exactly what you get, which I believe is something like 4.78 times 10 to the minus 19 coulombs, which is about 4.8 times 10 to the minus 19 coulombs. Make sure you show this. That's what they're looking for. Okay, and the last part, right, of this here question is the oil drop splits into 2 parts of equal mass. Both are charged. What's the net charge in each point? I should just divide this by 2, right? Well, hold on, maybe not, because remember we're talking about the oil drop experiment. They haven't asked me about the whole conclusion of the oil drop experiment, which is what they really want me to know about. And remember what we learned here is that the charge is quantized. So this is a stretch. This is, again, a very think on your feet thing. But they are hoping you notice that this is 3 times the elementary charge, which means my oil drop has 1, 2, 3 extra electrons on it, giving it that total charge. So when it went through the tube and there was friction, it picked up 3 extra electrons. That's it. And I got this little teeny tiny bit of charge. But the whole idea is that the charge can't be split. The whole idea is that charge is, we say, quantized. The charge, so here's another one. We might do some combination of writing and mathing. The charge on the oil drop is 3 times the elementary charge. Since charge is quantized, the elementary charge cannot be split. 1 droplet, 1 piece maybe, a charge of negative 2e, and the other will have a charge of negative e. So, right, so together they have to make up that negative 3, those 3 electrons, but it can only split up in a way that 2 electrons go one way, 1 electron goes the other way. There's no other way it could work. Both are charged. They have to say that because it's not one gets all 3 and 1 gets none. That could happen, but it's not happening here because of this. So, oops. Okay, so the charges are, we should probably just write out the numbers to be safe, 1.6 times 10 to the minus 19 coulombs, and 3.2 times 10 to the minus 19 coulombs. All right, again, very great if you notice that on the exam. That's tricky, but do keep the point of these experiments in mind. If they're asking about the oil drop, they're going to ask us about quantization of charge. If they're asking about the Geiger-Marsan experiment, they're going to ask us about the nucleus of the atom, that kind of stuff. Quickly, let's check our mark scheme just to make sure we're paying attention to exactly what the IB is looking for. That's the best way to practice. Okay, so for our picture, they're looking for equally spaced arrows all pointing down, and that you show these edge effects. Check, check. Second one, super nice, E equals V over D. We just show that we're using that equation, plug it in the values, and we show our answer. We get a point for the answer. Great. Okay, they need a lot here, surprisingly. So here they want us to say friction, definitely. and like where that friction comes from. So did we say it? Yes, the tube. So what's the friction? So you could say between the drop in the tube or the drop in the air molecules, something like that. Okay. The next one, this is the whole crazy weight thing. They want us to show, we have to show that the weight of the oil drop, we got to clearly show that this is density of oil drop times G times V. That's got to be in there. Then they say we should do some kind of ratio like this and show that the ratio is equal to the ratio of the densities like we did. And then you could either solve for the fraction to show like the number of that ratio, or just say the ratio based on this density ratio. You could just say in words the ratio is way less than 1. We're looking here for the weight vertically down and the electric force vertically up. You get a point if you just identify the two correct forces, and you get a point if you identify that we're in equilibrium here. Those forces are balanced, same length. Okay, then notice here, again, they're trying to like make sure that you're not just like, oh, it's the buoyancy force over E, so I just plug this in and do E. You have to show in this part, implicitly, they say at least, that I'm showing that the mass of the drop is what I'm dealing with here. So you need to show like mg or something and show that you're substituting this in for m at least, to show that you understand this isn't a buoyancy force, it's the weight of the drop in a weird way. We get a point for saying negative, great. Okay. And for D, they want us to say, this is interesting because they have 3 marks here. This mark scheme is kind of a mess in a couple places, but okay. They want us to say the net force is 0 because we're going to constant speed, and then say something like acceleration of the drop is 0, or, oh, I see. It's either these two things or these two things, right? So you either say the net force is 0 because the acceleration is 0, or that the net force and weight must be equal, and this is the weight and this is the net force. Okay, and finally we get a mark if we realize that like this is the move to do like the electric force equals this force and solve for Q in terms of variables. They then give us a mark if we show that we're plugging in the right values, and they then give us another mark if we show the unrounded answer to at least 3 sig figs to show that we got about 4.8. And last, they're looking for us to say charge is quantized, and so therefore 1e and 2e. Okay. Okay, last question here is a doozy, another big mega question. We got a mass on a spring mass oscillator. We're looking at some simple harmonic motion to start, and they want us to start by stating the equation of motion. Okay, this is an HL question, so we might be thinking about looking down here as we look at this, because we got a graph with the sine or cosine something happening, and they want us to write an equation for it. I should be thinking about these. These are our equations of motion for something doing SHM. Okay. I have some issues with the way they write the mark scheme for this, because this is not really set up in the problem of how they ask it, but whatever. We're going to write it out. The thing we want to know, though, definitely, like this is height with time, which is really like basically displacement or position over time. So this is like, a meters thing. So I want to look at this first equation. Like it's going to start with x equals xo sine omega t plus v. Okay. So this is like what's going on. All right. The phase constant here, phi, the phase constant is like the whole thing about the horizontal shift, right? The way they do this is kind of funky because they like just say you're going to use a sine function here, and then you adjust this to account for your starting position. Well, this is a sine function. We want to know definitely that sine is the one that looks like this. And so sine assumes you're starting at equilibrium. If you're not starting at equilibrium, which we are not, you need to figure out what to put here to account for your phase shift. So, hopefully you have some experience with this from math class. But what it is that's your horizontal shift. It's the weird thing where if like you add, it moves backwards. So I kind of picture it like this. Do whatever kind of math you need to do to get to this place. But if I'm trying to picture the sine wave, it's like the sine sort of cycle starts here. So it's kind of like I took a sine wave and shifted it back this much. And I shifted it back by 1/4 of a cycle, which is pi over 2. So my phase shift is pi over 2. Right, like sine and cosine are pi over 2 out of phase. So this is going to be pi over 2. I do want to substitute in as many other like things from the problem as I can. Like instead of x, they're saying it shows height with time. So instead of x, I should say h, because it's really height. And x0 is a, the amplitude. Okay, now if you ask me, h equals a sine omega t plus pi over 2 is a beautiful, complete answer to this question as written. Because like omega is your angular frequency. We know what that is. For some reason, they say don't accept the use of omega or x or any other symbols unless explained. This I get because you want to say h. We're talking about h. But like, what the heck? Why? Why? I don't know why. I think that's dumb. But they're looking for us to put this in terms of, I think because they said period somewhere here. So they just want us to make sure we include the period in here. I guess. Okay, fine. So we're going to put that in there. We just want to use the other equation in the data booklet of what angular frequency is, which is kind of this guy. Angular frequency would be 2 pi over the period. So that's going to go in here. And we're going to get our h equals a sine 2 pi over period times the time plus pi over 2. That's the equation that describes this graph in terms of all the variables happening in the experiment. That's 1 point. Yeesh. Okay, this one's 2 points and is a little maybe nicer because we love motion graphs, right? Sketch on the axis the variation with velocity with time, labeled a peak value, appropriate expression. Here, at least they tell me, in terms of a and t. So, okay, I have a displacement versus time graph. I want to sketch a velocity versus time graph. This is great classic physics. I love this. I know that velocity is the gradient of this graph, the slope of a tangent line, the derivative if you're a math nerd. And so at the beginning here, graph starts flat, velocity equals 0. Then I got a negative velocity. Then I got 0 velocity. Then I got positive velocity. And it should be no surprise to anybody at this point that if you gradient, aka derivative on a cosine graph, you get yourself a negative sine graph. It starts at 0, then it goes negative, then it's 0 again, then it goes positive. So the velocity starts at 0, and then goes down to some negative thing, and then back to 0, and then a positive thing, and then back to 0. I would want to, like, I'm going to do my best here. On the exam, I would, like, take a ruler and really make sure I, like, split this up nicely. Would be a good thing to do. All right, I'm going to do my best, but it starts here, then it's going to go negative, and then it's going to come back here, and then it's going to go positive, and then it's going to come back here. We want to make sure we're showing that the whole cycle, like, we know what a whole cycle is and that it takes a period to do this. Okay, so again, that should make sense looking at this. I'm thinking about the slope of the graph. Velocity 0, negative velocity, velocity 0, negative or positive velocity, velocity is 0 up again at the top. Okay, and they say also label the peak value on the v-axis, which is our y-axis, with appropriate expression in terms of a and t. The peak value, I'm going to my peak, and I'm going to go like this to label the height of that peak. That's the amplitude in math terms, but now it's like my velocity amplitude. It's my maximum velocity, so this is really Vmax. What's Vmax equal to? Well, let's look at our velocity equation. V equals omega xo cosine yada yada. Okay, the cosine thing, now this would also be pi over 2 because I got a negative sign, so the phase shift is still the same. But remember how this like math works? This is the whole thing that like waves back and forth between 1 and -1 and 1 and -1. And this is like the amplitude of the math function. So this is your maximum velocity. And that's a common enough thing that you want to know how this works. Like, because of how the math works here, the max velocity is just this thing out in front of the cosine term. In other words, the biggest amount all this can equal is 1, right? So at a maximum, this equals 1. So the velocity at the maximum equals this much. So it's angular frequency times x0. But we're like, okay, wait, they're saying a and t. Well, x0 is a, right? x0 is the amplitude. And we did this already, that omega is 2 pi over the period. So I'm going to write this as 2 pi times x0 over the period, because it's angular frequency, 2 pi over period, times, whoops, the amplitude, I should say a, not x0, because that's what they told me to do. That's the height of the peak. Okay, now they're like, this problem is so silly, because they go, okay, some simple harmonic motion. Now, wind can make a sea wave. This is the same question. Why not? Sea waves are produced by wind and carry energy that can be transferred into electrical energy. We got a wavelength and an amplitude and a width. So this we're picturing it as like a square, almost box wave. Show that the gravitational potential energy of the sea wave is this whole thing. Okay. This is the density of the seawater. They're going to do densities here. I'm thinking we're already doing some density times volume thing for mass again, because I'm thinking for potential energy, I really just want to do mgh. That's what I want to do. Well, let's see. What's m? I don't have an m in this. I'm just trying to like reverse engineer this and make this happen. I'm just trying to, play the game of getting to this answer. And I see like density. So this is again the whole like density's mass over volume. So mass I can replace with density times volume. And I might see where they're going here, because a volume is like the volume of this cube. And that's how I'm going to get all this junk in there. So that would equal density times volume times g times h, which would equal density times, let's see, what's the volume? Length times width times height. It's the wavelength over 2 is one side of the, cube, square, prism there. A is the other length and W is the other length. So that's my V. And then I got GH. I'm getting kind of close, I think. I just am missing a little bit. And the thing I notice is there's no H in here. So what height am I talking about? This is a little tricky, but all of your mass is all spread out throughout this whole little square wavy thing. So all of the mass is not at any one given height. But when we do this kind of thing, this would be a fair case to treat it as a point mass. It'll math out exactly the same as if we say all of the mass, potential energy-wise, could be concentrated right here. And if you had a point mass with the total mass equal to the mass of all the water in here, at this height, it'd be the same as the total amount of potential energy all these little water molecules have if you added them all up. So we're going to treat it like a point mass at a height a over 2, right in the middle. Right? Point mass means all the mass is concentrated right in the center of the thing. So we're going to pretend all of the mass is like right here. So our height is a over 2 is going to be, I think, the thing that puts this all together. So I put that in here, and let's see, do I get it? I get potential energy equals the density times the wavelength over 2 times A times W times G times A again over 2. I got my A squared. I got my over 4. I think we're good. 1/4 density A W. Oh, I lost my wavelength. That was here. Oh, no, it's there. A squared. What did I miss? I'm missing something. G. We did it. We did it. Okay, weird one, but it's just MGH, and then try to make it look like this. All right, the wave is moving at a speed v. Maximum power available is p. Explain why the maximum power per unit length available from the sea wave is this. Oy vey, this is 2 points, 2 marks. This is going to be a lot of stuff. You might have another way to say this, but I'm going to math through it. This is way too much work for 2 marks. I wouldn't actually do this on the test, but let's do it. Power over width, why not? Okay, I want to start with power. The one thing to start with power, always think it's energy over time. That's what power really is. That's the most important definition of power. It's not F times V. So energy over time, I just found an energy thing in the previous question, so that's kind of where I'm thinking. And so the energy over time situation is that potential energy I just found. So the potential energy, let's put in that whole mess that we had a second ago. This, W wavelength A squared, and all of that over whatever T is, whatever time we're talking about, the time it takes to deliver all of this energy, the power per length of the wave front. Okay, how long does that take? How long does it take as that thing is moving? How long does it take for all of that energy to, like, cross a certain spot? Well, it's going to move through half a wavelength. What's the time it takes to go half a wavelength? What's the time it takes to go a whole wavelength? That's a period. So the time we're talking about is 1/2 of a time period. Might be something. Sorry, that was 1/4 before. So we're going to put half a period down here. I think that's going to get me to my 1/2. I got 1/4 over 1/2. All right, there's no big T. There's no period in here. I also notice there's no wavelength in here. So I got to somehow get rid of wavelength, period, wavelength. Also, there's a V in here for the wave speed. Oh, maybe, I don't know. Maybe that makes us think of this good old equation, the wave equation. And remember, frequency is 1 over period. So another way to say this is that V is wavelength over period. So period is wavelength over V. So I'm going to do a whole mess of math now. I'm going to take this and put it in for period. I'm going to take all this and put it in for time. And then math. Okay. So I get like a quarter density G W this A squared over half of the period, which is this over this. All right, how does math work now? Fractions, well, a half and a quarter, that turns into a half. Lambda, that cancels out. Now this is 1 over V, so I'm going to bring the V up, and I think I get 1/2 rho G W A squared V, which is looking almost like this, and that's the power, remember. So I'm showing this is the power that comes out, and so the power per W, why not, is just divide away the W, and it's, everything there except the W. And I got their stupid answer. Okay, let's keep going. All right, now this is the same problem, apparently. Now, also, here's another way you can make energy. Let's just say it's still number 10. Thermal energy is also used in the production of energy. So there's a couple ways you could do it. You could burn stuff and do chemical energy, or you could do fission and use energy to make heat. And they give us a fuel and the temperature of a steam turbine. And then let's talk about the second law of thermodynamics and why is the efficiency have to be less than 60%. That 60% must be something I can figure out because that's not like a special number really. So I'm starting to think about how could I get a percentage number to make an argument here. And also, what's the second law of thermodynamics? There's like 15 ways to say it. One way to say it, since we're talking about efficiency, is that the second law of thermodynamics states that the efficiency of a real process, or maybe a real cyclical process or something, will be less than the ideal efficiency of a Carnot engine. Since we're talking about efficiency in the second law, that should come to mind, the old Carnot equation, because this is like the maximum possible efficiency of like a perfect heat engine. And we know entropy happens, nothing's perfect. So this is the upper limit. And I bet you that upper limit is going to be about 60%. So let's figure it out. All right, now be careful. I got just T's in the equations, not delta T's, and they gave me T's in Celsius, so I have to turn these into Kelvin before I put them in that equation. 550 is going to be 823 Kelvin. 30 is going to be 303 Kelvin. So let's find that theoretical maximum efficiency. It's 1 minus the cold temperature over the hot temperature. And indeed, when I do this, I get like 0.63. So I can say that's the max theoretical efficiency, and I know it's got to be less than that. So that's why they say less than about 60%. Okay, second law, entropy, Carnot, that's the equation to try and do some stuff with. Things are getting weird here at the end of the paper too. Okay, then they give me like this whole thing, which is I'm basically going to use this because you don't get a periodic table. So if I need to figure out an element, I'm going to come back here. And it shows me all the possible like isotopes. In a fission, two nuclei are produced together with several neutrons. One of the things produces a this guy. State the reaction. Well, okay, let's look at what happens here. The fission is induced. This is an easy thing to mix because way up here they tell us this is neutron-induced fission, which is how things work in a nuclear power plant. You do want to know. So a neutron comes in, crashes into this uranium here, and then I get my products. Okay, so my reaction has to start with a neutron crashing into uranium-235 if I like read through all that junk. So 235 U92 over here, and I also have a neutron. Remember, write it like this. Bottom left of the charge of a neutron is 0. Top left is neutrons plus protons. There's one neutron plus proton in a neutron. Okay, that's what I start with. They also give me one product here. So I just got to balance this now. Okay, so it's a little bit of a puzzle, but I know that there's going to be, it's emitted with several neutrons. So there's going to be some other something here, because definitely like I need to get 92 on the bottom. And there's also going to be some number of extra neutrons. And that's what I have to figure out. Well, I don't know this until I know this. Like you kind of have to do it in a special order because the one thing I know that I can start with is that the bottom numbers have to add up to 92. And the neutron bottom number is always 0. So it doesn't matter if I have 100 of these, it doesn't change anything about the bottom. So just what is the element that's going to make this part balance? What's going to be, I need 92 minus 56. So I need a 36. I need to come up to my little table here. My little cheater periodic table and be like 36. That's krypton, I think, Kr. Okay, Kr36. Now, the question is, how do I know which one? It's either 86, 87, 88, or 89. Which one is it gonna be? Well, it's produced with several neutrons. All right, so how are we gonna pick what it is? I'm thinking there's going to be a couple possible answers here because I just need the top numbers to balance now. And there might be a few ways to do that because let's see, 236. You need 236 up top because the left side totals 236. So it's going to be 147 plus however much for the krypton plus however much for how many neutrons. Several, I don't know, let's say it's 2. Let's say there's 2 neutrons. Let's just check that. I'm kind of guessing and checking at this point. So 147 and 2 is 149. If I do 236 minus 149, I get 87. So one possibility is I could have maybe 87. Does that work? Is that a thing? I'm just checking if that's like a possible isotope. And yes, it is. That would give me this. Okay. I think, though, I could also, looking at this, like 86 seems like it's also possible because you could have 86 and 3. And indeed, both of those are possible. They'll take either one. So let's just pick one and move on with our lives. So I'm going to put 87 here. And that'd be 2 neutrons. And I'm like, okay, I'm going to check and make sure everything adds up here. Top and top are both 236. I'm going to check that my bottoms both add up to 92. I think I've done it. Okay, on average, the fission of an atom of uranium releases 200 million electron volts. The energy density of coal is approximately 25 megajoules per kilogram. Estimate the ratio energy density of uranium to energy density of coal. I know it's like a bajillion because that's one of the big advantages of nuclear power is that it is super, super, super energy dense because you are splitting the atom to turn mass into pure energy. And then you're like boiling water. But you know, you can get a lot out of a little bit. Energy density, remember, is this kind of thing, joules per kilogram. Sometimes we call it specific energy. The IB decided they don't care anymore. But joules per kilogram is like energy density, basically. Okay, so we want the energy density of uranium. So how many joules per kilogram? Well, this much for 1 atom of uranium-235. So what I need to know, that's the amount of energy. I need to know how many kilograms is an atom of uranium-235. And it's like barely any kilograms because it's a single atom. It's super small. This one, you got to like kind of make an estimation, and they're telling me to estimate the ratio, so this is fair. But uranium-235, like the mass of uranium-235 is not like straight up in the data booklet, but I want to know what it is. It's 235 protons and neutrons, you know, all smushed together. And each proton and neutron basically has a mass equal to the unified atomic mass unit, 1 AMU. So I think a good estimation would be to say the mass of a uranium-235 is about 235 atomic mass units. That seems close enough to get an estimate. So let's do that. So let's do 235 times this whole number. For the amount of mass, and that's 3.9 times 10 to the minus 25 kilograms for 1 atom, 1 nucleus of uranium. I also want, so I want to compare joules per kilogram to joules per kilogram. I got my energy in mega electron volts. Remember, you have to be able to convert from electron volts to joules, which is not in here. You got to know 1 EV is 1 E times 1 V. It's an elementary charge times a volt. As a volt's a joule per coulomb. This gives you your energy in joules. So an electron volt is this many joules of energy. So 200 million electron volts, I'll do it like this, times 10 to the 6 electron volts is what the mega part means. And I'm going to then multiply because there's this many joules in 1 electron volt. So what does this give me? 3.2 times 10 to the minus 11 joules. Okay. So the energy density of uranium-235 then is this many joules over this many kilograms, 3.2 times. I could probably really just do power 10 stuff here, I think, for an estimate, but let's plug in the numbers, see what we get. 3.9 times 10 to the minus 25 kilograms. And when I divide these up, I get 8 times 10 to the 13 joules per kilogram. Okay, so I found the energy density, because energy density is joules per kilogram, so I had to convert this energy to joules, figure out the mass of the uranium in kilograms. Now I'm partway to earning these 3 points. So much work for these last couple problems. Don't spend a lot of time here. Go get those easier ones. But, all right, now I got to find this ratio. So there's the energy density of uranium. I have the energy density of coal. Be careful with the mega here. So our ratio that they're asking us for is this divided by the one they gave me, 2.5 mega joules per kilogram. It's so much bigger, 10 to the 6th, 10 to the 13th. It ends up being about 3 million, 3 times 10 to the 6. 3 million times more energy dense than coal, uranium is. Okay. All right, let's try to finish this thing off. Now some other energy stuff. Also, a star has energy from nuclear fusion. Attempts are being investigated to use fusion on Earth to provide electrical energy on a large scale. What's one advantage and one difficulty for this becoming a reality? This is a knowledge thing. Do you know about fusion? Do you know the benefits? Do you know why it's tricky and we're not quite there? We've done it a little bit. We got ignition just a few years ago. It's pretty exciting. Okay, so one advantage, you could say any number of things here. Fission, how about this? Fission does not produce any radioactive byproducts. You're just smashing hydrogens into heliums. You don't have nuclear waste to deal with. So no nuclear waste to affect the environment, something like that. We could also say it's super. You get a ton of energy out of fusion, even more than you, you get a ton of energy out of fusion, way more than you get out of fission. That's another thing you could say here, any number of things. And I guess I should spell this out, shouldn't I say? So I should say one advantage of fusion is that it does not produce any radioactive byproducts. Okay. One difficulty for fusion on Earth is, again, there's a couple things you could say here. It's got to be super hot, is like, let's say, containing the hot plasma goo, the hot plasma where for the reaction. Something like that. Okay. There's two things. Be careful. They say identify one advantage and one difficulty. Do not list a bunch of things to show how smart you are and how much you know about fusion. They will not give you credit for it. They might even penalize you for it because you're not doing what they asked. Okay, and the last question on the paper 2 here is a little weird. But so they basically said in this whole big mega problem that we decided to make one problem, we just talked about a whole bunch of different ways you can make energy. And they definitely want you to know about, like, especially this stuff. C waves maybe are less common, but like fossil fuels, then fission and fusion. Like, what are the advantages, disadvantages? How do they compare? There's a ton of things you could say here. So we're going to look at the mark scheme for this one. And the mark scheme for this one is like especially cruel because there is something they want that is not in the prompt, I would say. So I think this is like a big issue with this specimen paper if you're asking me. But anyway, what they want is they want you to call back to like some data from previously. So let's start there. Here's what they want. For 3 marks, you want to just be talking about all 3 methods, referring twice to some data described during the question with appropriate concepts. So they want you to call back to, and like there is some hints here that because they say, talk about the efficiency of the methods. Well, we found the efficiency. We talked about the maximum possible efficiency of like a steam turbine, which is what you're producing when you do this kind of stuff. So we could talk about efficiency there versus efficiency, say, of C waves, which don't use steam spinning a turbine. We found energy density numbers here, so we could talk about, like, a good thing to say is uranium is 3 million times more energy dense than coal, which is a big advantage of uranium versus coal. They want us to be mentioning that data, though. If we don't mention any data from the question, we can only possibly get 1 mark. And if you just refer correctly one method and making reference to at least one correct concept related to efficiency, impacts, or availability. So if you say anything correct about efficiency or impacts or availability of any of this stuff, you get 1 point. If you compare at least 2 of these methods with some good stuff, and you also pull in 1 piece of data, like you talk about this energy density thing, that's 2. And if you mention 2 pieces of data, that's worth 3. I don't think the question is written well at all for that to be like clear that that's something you're being asked to do, even with the command term here. But that's just my little rant. But that's what they want. All right, so make sure you know generally about these things. You know, coal, very bad for the environment. Not super efficient, like 30% efficient or so, but pretty available. Right, fission is like the uranium reactors, right? So environmental impacts, there's radioactive waste to deal with, but no carbon emissions, no greenhouse gas emissions. Fission is honestly generally very clean energy, even though we got to discard some nuclear waste. We got some pretty good ways of doing that. Fusion would be like have very, very, very little environmental impact because you got none of those things. Fusion, like we talked about, is difficult to do. Fusion is very inefficient right now. We're working on it. So that's the kind of stuff you would want to talk about. Let's just check the rest of the mark scheme for number 10. Let's go back to the very beginning. And we'll call it a day. Okay, so way up here, here's where they say this dumb thing about how you're supposed to write that equation. That is what it is. All right, if we draw a negative sine curve here, you get a point as long as the period is t. And this is what we should figure out for the amplitude. There's 2, the peak value, there's 2. Oh, here they'll take omega, look at that. Okay, so this one, they're saying like for finding the different pieces. So if you identify that the mass is density times volume, which is density times this stuff. So like for this step, you get a point. For recognizing that you can do center of mass at a height of a over 2, you get a point. And if you put it all together, get the answer, you get a point. Then for this one, they want you to, they do it a little strangely here, a little differently here. They're still doing, yeah, energy over W with the T thing on the bottom, for like a whole period or something. But then they're saying in that period, you also get some kinetic energy, which is the same rate as gravitational potential energy. That's pretty weird to me, but that's one way you could argue it. I would assume you would also get marks for this, which is a more algebra way to muscle your way through that weirdness. In this one, you get a point if you identify the efficiency, the theoretical efficiency. That's got to be 2 sig figs or better for credit. Again, because they're saying about 60%, this is kind of like an implied show that kind of thing. So you want to show the exact number that's about 60%. And then the second law says like there's a maximum possible efficiency, something like that. Okay, for this one, you get a point if you recognize the correct elements just by balancing and getting a 36 here. You get the second point if the whole equation is correct with the neutron over here and either 2 or 3 neutrons over here. So as long as this balances, you could have like an 86 and a 3 or an 87 and a 2 because they are both possible. Okay, this one, they give us, there's a whole bunch of like ways you can do it. So one way, I think, is this the way we did it? This is the way we did it. So we found the energy density of uranium and then found the ratio. That's how we did it. You could also, what are they doing? They're finding, yeah, they're doing like, oh, they're doing how many joules in a mole. And they're doing some mole stuff. I like our way better, but that's another way to do it. Okay, and then here, like they say, any suitable one of either one. So no radioactive fragments. It's ready available fusionable elements because there's tons of hydrogen everywhere. Hard to contain stuff, or you need really hot temperatures. Those are the 2 big ones. And like we said for the last one, apparently talk about some data. Okay, well there you have it, a paper 2. You know, again, remember the paper 2, you're not supposed to get everything right. You're not going to get everything right. The average person gets 30 to 40% right. So you want to pick a couple things to feel really strong about. Pick a couple topics that you can nail, where you can really dig in and, you know, get to this level of detail on some topics. And if you can do some stuff, you're going to do just fine. All right, so keep at it, get studying, and good luck. Have fun.